is
Is
going
it?
on, sir. But
I guess it is a seminar hall or something, sir.
yeah. I got some space. Yeah, I
Thank you.
requested them space actually to start.
Another 2 minutes to go, sir. We will start.
No problem, sir.
Relax, relax,
Absolutely
sir.
okay.
Chennai seems to be very humid, I guess, sir.
Very humid, sir. I just switched on the AC.
Yes.
I'm just checking which way is good.
It is good, sir.
It's
No
a
problem.
hall. It's a hall.
Oh, how was conference going, sir?
It's a workshop, sir. Leadership workshop.
Okay.
Only for directors and deans and pro vice chancellors.
Okay, okay. And slowly the participants count will also increase, sir.
Mhm. It's
Slowly
okay,
it will
sir.
rise, sir.
No problem, sir. Single person is also okay for us.
Yes, sir, sir. They are all very much eager to listen to you, sir. Definitely.
Great, sir. Great.
Sir, shall we start, sir? Do
Yeah,
you
you
have?
can start, sir. No issue,
Yes, sir.
sir.
Yes, sir. Dear participants, good afternoon to all of you. Today we have with us an eminent speaker, my friend also, Dr. Raviraj M. Kulkarni, sir. And it would be my really, I feel it privilege to introduce Raviraj sir to all of you. So here is a brief introduction. Dr. Raviraj M. Kulkarni, currently Professor and Director, IQAC at MIT Vishwaprayag University, Solapur. Earlier to this, he served as a professor and head Department of Chemistry, coordinator Center for Nanoscience and Nanotechnology, and coordinator for BSc Honors Program at KLSVDIT Institute of Technology, Belgavi. He is also chairman, Board of Studies in Nanotechnology, and Dr. Kulkarni did his PhD from Karnataka University, Dharwad in January 2003 and postdoctoral research work in University of Leuven, Belgium, University of Alberta, Canada, and TIFR Mumbai during 2003 to 2007. His contribution in the field of nanotechnology is outstanding. 26 years of teaching and research experience stands to his credit. Dr. Raviraj sir has successfully guided 5 PhD students and 70 BE and MTech final year projects. Dr. Kulkarni has published 199 research papers in prestigious national and international scientific journals and 2 design patents granted. He has 2,972 citations to his papers and his H index is 29. Dr. Kulkarni has delivered more than 200 invited talks in national and international conferences and seminars. He is certified trainer for Skill India. He has received prestigious Young Scientist Award for the year 15-16 from VGST, Government of Karnataka, and he has also received award for research publications from Government of Karnataka. winning grants from many funding agencies at the state and national levels. He has completed many research projects. Dr. Raviraj Kulkarni has organized many national and international conferences as convener. Dr. Raviraj has established a Center of Excellence in Nanoscience and Nanotechnology at KLS Gopte Institute of Technology, Belgavi, to provide a platform to young researchers of GIT to carry out research in the field of nanotechnology. He was invited by Synod College and Basin Development Authority of Government of Meghalaya as an expert for water resource management and treatment. Dr. Kulkarni is a scientific advisor to Glutrac Private Limited, who are into development of devices for non-invasive glucose detection. Dr. Raviraj Kulkarni also served as an external examiner for University Putra Malaysia and King Abdulaziz University, Saudi Arabia. He is nominated as chairman, Board of Studies of VTU Belgavi. He is a member of expert committee of VTU for revamping first year syllabus constituted by Professor Vidya Shankar, Vice Chancellor of VTU. He is a member of many professional bodies like American Chemical Society, Indian Council of Chemists, ISTE, IAAM, etc. He is also in the editorial advisory boards of many reputed journals. With this brief introduction, I now present before you today's resource person, Dr. Raviraj M. Kulkarni, sir. Sir, welcome you. Happy that you are here. You accept our invitation. Though you are very busy, I can guess, what is the schedule there. In spite of your busy schedule, you made it to come to our FDP. And on behalf of all the participants, I wholeheartedly welcome you, sir. Thank you very much. Now you
Thank
can
you.
begin your session.
Thank you so much, sir. Thank you all. And thank you, sir, for the wonderful introduction. Shall I just share my screen?
Yes, sir, you can.
This one. Yeah. Yes.
Sir, it is visible, sir. It is visible.
Visible, no, sir? Okay,
Yes, sir.
okay,
Yes.
great.
Only side show. Yes, sir.
Now you can see the slideshow, sir?
Yes, sir. Clear.
Very good afternoon to one and all present here for the FDP on semiconductor, I guess. And basically, I work in the field of environmental chemistry, nanotechnology, and my talk is on environmental impact, green technology, and future research ecosystem. I'm basically a professor of chemistry, and I was former chairman of nanotechnology board at VTU. And presently, I'm professor of chemistry and director IQSC at MIT Vishwaprayag University, Solapur. So before I start anything, I should give the history of nanotechnology. Nanotechnology in India, we have been using this, and many of us don't know that we are using nanomaterials. And these nanomaterials are there in our day-to-day life. You see, bhasma. And if you say Ayurvedic people, if you go to Ayurvedic people, they say bhasma. Bhasma is nothing but nanomaterial. Okay, we have Swarna bhasma, gold nanoparticles, Rajata bhasma, silver nanoparticles. Okay, so this is the first nanotechnology we developed long back, but see, we don't have in those times we didn't have the proof. Okay, so that's the reason in those scientists, in those days, we used to call them rishis and all. So they told that it is like something related to religion, and they made it compulsory to apply something on your forehead like bhasma or vibhuti we apply. we are used to apply. Nowadays many people we don't apply, right? But the main reason, okay, what is the scientific theory behind this, what why they are where I mean insisting applying Basma is because when somebody is suffering from cancer, what is the solution? If you go to um, any allopathic doctor, he will say surgery is the only option, or he will give some chemotherapy, and it's very difficult to survive most of the time. So if somebody has a tumor in his head, okay, so most of the drugs won't reach the tumor cells. They won't go there because we have a blood-brain barrier, okay, which prevents, okay, which supplies purest form of the blood to the brain. Okay, so these things are blocked. We have calcium channel blockers and all. They block and they allow only the purest form of the drug to reach from the blood to reach the brain. But these nanomaterials, they can cross blood-brain barrier. Okay, they, when they do yagna and all, they used to add ghee. Okay, so we call it as lipids. Okay, when we add lipid to nanomaterials, they can cross blood-brain barrier. And what happens? The cancer cells are the hungry cells. Okay, if somebody is on chemotherapy, you observe him or her, I mean, he will lose the hairs first. All the hair will go because fastest growing cells in our body are the hair. Okay, they go. So when this basma is applied on the forehead, it is absorbed and it is taken up by the fast growing cells. Okay, so that part, okay, we don't have any, right, what the hair, of course, and also the when right, hungry cells, they absorb it. Okay, when, I mean, earlier we used to be farmers and we used to go outside the this one, I mean, on the sunlight and all. And what happens in the sunlight? Okay, heat is there. Okay, and silver nanoparticles are there in the basma. Okay, if you observe with SAM10, EDAX, XRD, if you do that, you'll get the silver particles that are there. EDAX, if you observe EDAX. So silver nanoparticles are basically have the antibacterial property, and also they are easily absorbed by the that cancer cells. And when sunlight falls on that, okay, they are heated up first and they kill the cancer cells. That was the preventive measure they used to take long back. Okay, it's nothing to do with religion. Okay, people don't follow it. That's the reason they put it in the form of religion. Okay, that was the first history, and many scientific report publications are there. Okay, I don't tell anything other than the scientific things. Okay, right. So I'm talking about the history now, and we know Damascus word. Okay, Damascus word. Okay, you might have observed it's a double-edged sword, and it is made up. Right, they somehow incorporated carbon nanotubes and graphene in the sword. And in those days, okay, it's present in right, Austria now. Okay, Austrian museum. Okay, actually it's I mean, we got it from Damascus. Okay, Damascus is the capital city of Syria. Nobody would like to go there because it's a war-torn country, right? But in Austria, you can see this double-edged sword, and you can see that carbon marking there. Okay, somehow they incorporated carbon nanotubes, and carbon nanotubes are the hardest materials. Okay, graphene and carbon nanotubes are the hardest materials. When you incorporate in the normal wood steel, okay, so the strength increases. Okay, usually if you incorporate non-metallic things in metals, okay, the strength should decrease, but in this case it has increased. Okay, and in those days the blacksmiths, they developed this sword, and it helped them. Okay, a lot of crusades used to happen in those days. Okay, and they wanted to capture the Jerusalem, and these people, Syrians, they wanted to protect it. Okay, so the crusaders faced this sword, and this is double-edged sword. And you see, the normal sword is made up of steel, and this is harder than diamond. Okay, it's harder. Okay, when you hit the enemy sword, not just the enemy sword will also cut. The diamonds. Okay, hard materials, right? So that's the reason. Okay, the strength has increased. Okay, this is another history, and it is developed in India. Though we say Damascus word, this word, okay, was first developed in India, Sri Lanka. Okay, and there's a paper on this by Peter Puffler. He published it in Nature 2006. So nanotechnology is basically, okay, research based, okay, discovery, invention, and innovation, three types of research. And everyone knows what is discovery. Discovery is like there is something already there, you are discovering it. Okay, discovery means, okay, a scientist discovered a new planet. Marie Curie discovered radium. Radium is there in the nature, and we are discovering it. Okay, so you go to a party and one of your friend, okay, starts singing. He or she starts singing. What you observed, what you discovered singer in him. That's what it's called discovery. Because you may not be knowing that he's a singer or she's a singer. Now you came to know he's a singer. That's why it's called discovery. Earlier we were not knowing, we know it now. Okay, invention. Invention means first time we are developing something, okay, and right, with the known materials we are making it, right, arranging them, and we are developing new things like steam engine was right, invented. Wright brothers invented aeroplane and all those things. They are inventions. First time if you do that development, okay, that's called invention. A delta x, a small improvement in the invention, we call it as innovation. Most of the time we do innovation, not invention. Okay, these are the three different research. Okay, discovery, research, invention, and innovation. Okay, nanomaterials. Okay, it started with nano. What is nano? Nano means dwarf in Greek. Okay, which is extremely small. Okay, a nanometer is 1 billionth of a meter. Okay, 1 nanometer is 10 raised to minus 9 meters. Okay, according to IUPAC, nanomaterials are defined as a material having sizes in the range 1 to 100 nanometer. You may ask me a question here: why 1 to 100 nanometer particles are called nanomaterials or nanoparticles? Why not 100 to 200? That's also nano, right? But I'll discuss that why it's called nano. Okay, nanomaterials show different properties compared to the bulk counterparts. I'm just giving the brief introduction about what is nano. Okay, so they show different properties. Okay, for example, copper is malleable and ductile, normal in the bulk case. When you go to nanoscale, it is not malleable and ductile. You cannot make into wire or sheets. Okay, it becomes super hard material. Okay, gold is right, very stable compound. Okay, noble compound in the macro scale, but it's not the same in the nanoscale. Okay, so it acquires different properties at nanoscale. It becomes a catalyst or it becomes, active material at nanoscale. Okay, so I'll just give this how small is a nano. Okay, you have seen watermelon. Okay, its radius is 10 centimeter. You have seen a coin. Okay, 1 centimeter or so. Okay, a full stop you do, that's 1 millimeter. Hair, 100 microns. Okay, or 1 lakh nanometer. Okay, bacteria cells. Okay, 10 microns or 5 micron. Blood cell, 5 microns. Virus, 100 nanometers. Gold nanoparticles, 10 nanometer. Okay, a water molecule is 0.1 nanometer. Okay, benzene is 0.5 nanometer. So I'm just giving you the scale, how small is nano. Okay, carbon nanotubes are a 5 nanometer diameter. Okay, so you got some idea about what is nano and all. Okay, if you take one hair, okay, and cut it into 100 slices, take one slice, that is 1 micron, 1 micrometer, and take 1 micrometer and make 1,000 slices, you take one slice out of it, it is 1 nanometer. We cannot see nanomaterials with the bare eyes because of limitations. Okay, wavelength limitation. I'll just discuss that also. Okay, why properties change at nanoscale? Okay, it is because of electron confinement, called quantum effects. Okay, and greater surface area to volume ratio. Okay, reduction in solid state defects. Okay, surface and interface forces become dominant. What do I mean by this? Electron confinement, greater surface area to volume ratio, reduction in solid state defects, and surface and interface forces become dominant. Okay, I'll just tell you what is that confinement effect. You take a box, three-dimensional box. Inside, okay, electron, say it's a solid box, it's a made up of it's a metallic box. Electron can move in X, Y, and Z direction. Okay, it can move in X direction, Y direction, and Z direction. All the three possible directions. Okay, so imagine I have a cutter. I can cut a slice of this three-dimensional box. What I'll get a sheet. I'll just sheet. Okay, the thickness I'm cutting, imagine I can cut in nanoscale. Okay, the thickness is in nanometer. So it is thin film. Okay, 2D, two-dimensional. So electron is confined. So it can move in positive x-axis and y-axis. Okay, right. Now z-axis is confined. Okay, then you take that sheet and cut the edge. Okay, you get a string wire. That is 1D nanowire. Okay, one-dimensional object. So the electron can either move in x direction, positive or negative x direction. Okay, take that string and cut the edge, leaving all the dimensions at nanoscale. We call it as nanoparticle. Okay, this everyone knows, but I'll just give one more analogy. Okay, so I'm in a room. Okay, I can move freely everywhere. So it is three-dimensional space. What I do, what happens is if the ceiling is brought here, now I cannot jump because this motion, Z motion, is stopped. Okay, now I can move in X and Y direction. Okay, so two-dimensional object, that is thin film. Okay, if I bring, okay, the other two walls here, so right, my direction I can go back and front. That's it, one direction. So that is one dimensional. So if that wall, back wall also is brought here, ceiling is here, two walls are here, and the back wall also I'm bringing here. So I'm totally confined. So it is zero dimensional. I don't have any space to move. So it's totally confined. Okay. So I'll give an analogy for this. It's called electron confinement, quantum confinement. Okay. Imagine there is a line. Okay. There's a line near your place. Okay. Now I request you. Okay, it has not taken food from last night. Okay, it's very hungry. Okay, I request all the participants to go and feed that lion. What is your reaction? You say no, we cannot go. Because first of all, it's a lion. Second, it is hungry. What is the property of that area? Fear is there. People are afraid. Okay, what I'll do, I'll call the forest people. Those people come and cage that lion. When the lion is caged, anybody can go. The property is changed now. The property is totally changed because earlier there was a fear. Now there is no fear. We go to zoo. See, we see the lion. Okay. So confinement, the properties change. Fear, earlier fear was there. There is no fear. So the properties like electrical conductivity was there. There is no electrical conductivity. Conductors may become semiconductors. Semiconductors may become insulators. Okay. So it's because of confinement. So we had a nano club earlier institute. Okay. So we received good amount of funding for our students. Okay. All right. Now next is surface area to volume ratio. Increase in surface area to volume ratio. What I mean by this? Okay, you see the first cube. Okay, you see the first cube is 3 by 3 cube. Okay, say 3 centimeter by 3 centimeter. Okay, what is the surface area? How many surfaces it has got? 6 surfaces, and one surface area is 3 square. So 3 square into 6 faces. So it is 54. 54 square centimeter if it is centimeters, meter, square meter. Okay, volume we say 3 cube. Okay, it is 27 meter cube, for example. When you take the ratio, what happens? The surface area to volume ratio becomes 2. 54 by 27. It is 2. Okay. Now in the second case, okay, sides are 2 sides are there. Okay, surface area is how much? 2 square and 6 faces, 24. Volume 2 cube. Okay, 8 meter cube. Okay, when you take the surface area to volume ratio, okay, it is 24 meter square divided by 8 meter cube. So 3 per meter actually it is. Or surface area to volume ratio is 3 per meter. I'll take another cube. Okay, I'll just break it into another cube, small cube, 1 cube only I'll take. The size are like 1 meter by 1 meter by 1 meter. Okay, now surface area is 1 square into 6 faces, right? 6 meter square. Volume is 1 meter cube. That's 1. 6 by 1. 6. So when you decrease the particle size, surface area to volume ratio increased. Now imagine. Now you are going to a nanoscale. Okay, imagine the last one, the one, if it is 1 nanometer. 1 nanometer side. Okay, one sides are 1 nanometer. So 1 nanometer by 1 nanometer by 1 nanometer. What is the surface area? 1 nanometer square. 1 to 10 raised to minus 9 square meter. Okay, 1 into 10 raised to minus 18 meter square divided by volume. Okay, 1 nanometer cube. 1 into 10 raised to minus 9 raised to 3. Okay, it is 1 into 10 raised to minus 27. Okay, when I take that 1 into 10 raised to minus 7 to the numerator, it becomes 1 into 10 raised to 9 because minus 18 plus 27, it becomes 1 to 10 raised to 9. So surface area becomes, okay, the box surface area or surface area to volume ratio increases by 1 into 10 raised to 9, 1 billion times. Okay, so surface area becomes huge. Okay, I'll give an example. See, when you go to flour mill, we take a small amount of, half box full of grains, but after grinding, it becomes full. But if it is nanoparticle, you need three or four of boxes, this kind of boxes. So surface area becomes high. That's the reason you require more boxes to fill the powder. Okay. So here also we use in right mobiles. Okay, what happens? Okay, can you recharge your smartphone battery? Right, we usually do every day. Why? Smartphone battery needs recharging every day. We use very high applications, right? So can you recharge? Can you recharge your mobile once in a year? Lot of super capacitor, of course, the batteries. Okay, the right, when you coat it with nanomaterial, surface area increases, they can hold large amount of charges. Of course, there are a lot of issues. Still, we have not reached that much, but in future, it comes that once in a year we can recharge our mobile. Not now. Okay. Can you charge your mobile within a fraction of a second? Yes, nowadays supercapacitors are in the market. Okay, supercapacitors, because surface area to volume ratio increases. Okay, basically two conductors we use. Okay, in parallel plate capacitor, if you imagine, okay, if you coat nanoparticles on the both sides, what happens to surface area? It becomes square kilometers. Okay, surface area becomes huge, A by D. Okay, A surface area is huge. Distance between the two electrodes is very close by. So you get very high charge. You can store up to 10,000 or 20,000. Okay, right, farads. Okay, 10,000 farad means 10,000 into 96,500 coulombs. That much charge you can store in a right supercapacitor. And supercapacitor, it discharges quickly. You can recharge your mobile within a fraction of a second. Of course, there are battery management systems should be placed. Otherwise, it will burn your mobile. Okay, so this industry is growing like anything. And you see the first nanosensors. Okay, nanosensors, of course, sensors we use in all our right diagnostic tools. Okay, all right, environment is right getting polluted. Okay, right, we are using sulfur dioxide sensors. Okay, to monitor the quality, carbon dioxide sensor, carbon monoxide sensors, many sensors. Okay, they are all based on, they are resistive sensors, capacity sensors, optical sensors. Okay, electrochemical sensors. Okay, you can see the first guy. His name is Ben Johnson. Okay, I remember I was just 8 years old at that time in 1984. Okay, he won all gold medals. He was a Jamaican born. He's a Jamaican born Canadian sprinter. He won all gold medals. Okay, in 1988 also he won all the gold medals. Next Olympic also. Right. Later, it was discovered, it was found that this guy was taking performance enhancement drugs, but we didn't have the sensors at that time. Okay, so that's why he was escaping. But in 1988, okay, finally they found that this guy is taking performance enhancement drugs. So all the gold medals were stripped off from him. Okay, so that started with the sensor industry. And you see, if somebody is suffering from asthma, what we do, what we ask them to, right, breathe out the air from the lungs. Okay, if he has asthma, okay, instead of 2 ppm or 3 ppm nitric oxide, the nitric oxide concentration, the ppm will be more, okay, in the breath. Okay, so he is suffering from asthma or she is suffering from asthma. Okay, if somebody is breathing out acetone, he is a diabetic person. Okay, the sensors. Alcohol test. Okay, usually police do that. Okay, they ask you to blow air. Okay, blow this one. Okay, and so alcohol, if alcohol is there, it will give signal. Okay, so what is the use of nanotechnology here? See, in a stadium, okay, one of your friend is sitting in the stadium. Okay, and
Hello, sir. Sir, is there any interruption, sir? Hello, hello, hello. Raviraj, sir. Hello.
hello, hello, am I audible? Am I audible? Hello,
Yes, sir.
hello,
Yes, sir. Audible, sir. Now.
audible. Thank you. So can you see the screen?
Yes, sir. It is visible, sir.
Is it? Okay, okay. Yeah, some network issue here. I'm just
No
sitting
problem.
outside. Yes.
No problem.
Yeah. Yeah. So there's a stadium. There are 1 lakh people sitting, and one of your friend is sitting in the stadium. So what is the chance like this? 6 people. It is basically 10 ppm. Okay. Out of 1 lakh, you are finding one person. Out of 10 lakh, you are finding 10 persons. Okay. So it is 10 ppm chance. Okay. That's you want to search somebody out of say one out of 10 lakh, you are finding one person, for example. It is very difficult because it's so big area. And what do? You how to detect that person? You ask him to just switch on his flashlight from the mobile, right? Then he does like this. But there may be other people who will do the same thing. It is very difficult to identify, it's difficult to sense that person, find that person. Instead, you take a small room, okay, small room where there are only 9 chairs, okay, 10 chairs, and your friend is sitting, easily you can identify. That's the advantage of nanotechnology. Nanotechnology, the space available, okay, for one person, one space, you can do that. Okay, right? In bulk, there are so many people, you are identifying one person. It's very difficult. Okay, so that's another sensor industry. Sensor market is huge. Okay, it's 0.79 trillion. Okay, Huge market it is. So then semiconductor industry now, we are using semiconductor nanoparticles, okay, quantum dot sensitized solar cells. Okay, normal solar cells, okay, right, what they use silicon semiconductors, okay, and dope it with trivalent impurity, a pentavalent impurity, okay, N type and B type and all. Okay, so the disadvantage is, of course, even infrared light can excite silicon electron of silicon in the from valence band to conduction band. Still, you can generate electricity. That's the advantage of silicon. But silicon, to make one silicon wafer, you need to do a lot of work. Okay, of course, it is available in bulk because from sand only we prepare silicon. Sand is quartz silica SiO2. Okay, from there you just reduction and then you develop that semiconductor silicon. It's abundantly available, but the problem is the process. Okay, you need to do a lot of zone refining, and there are so many processes of purifying because you need 10 right 7N or 9N purity. 7N means 99.99999 okay, we call 7N purity. Okay, so it's very difficult to achieve because so many times you have to do iterations with right, that zone refining and all those things, right? So instead of that, can we go with right, like zinc oxide or cadmium sulfides, okay, like right, TiO2, these kind of nanomaterials, okay, which are N type basically, right? So what we do is basically on ITO glass, okay, conducting glass, okay, we do the conducting closest tin oxide, indium doped tin oxide or fluorine doped tin oxide, FTO glass, okay. So we can coat nanoparticles like TiO2 nanoparticles, okay, by simple Dr. Blade method, okay. So some of my students have done this small projects on this. Okay, they could able to generate like right 0.5 volt or something, not much, but single cell. We tested it. Okay, counter electrode, you can, if you don't have platinum, you can start with graphite. This one coating on the glass, it will work. Okay. So you require redox couple, iodine and triiodide, or sulfide, polysulfide. Okay, redox couples. Okay, for whole transport we say. Okay, so the mechanism is same, right? You generate, electron hole pairs are generated. Okay, and electrons, right, from N type. Okay, that TiO2 base side. Okay, that transmitted to counter electrode. That's cathode we say. And what happens? The holes migrate, and they come to this platinum counter electron. They combine with the electrons. So electricity is produced. Okay. So basically, we use there are two types of semiconductors. One is direct band gap and indirect band gap semiconductor. Okay. Basically, here we use indirect band gap semiconductor because when an electron is excited, it should not come back. Okay. We say like the efficiency of a solar cell is 20%. What I mean by that 20% is if you use 100-watt bulb, you are producing 20-watt electricity. Okay, what happens to the 980-watt? Where it is going? It goes as a waste, right? Because electron hole recombination takes place. When light falls, electron hole pair is generated, but again it recombines. So 80% goes there itself. Okay, nowadays quantum dot sensitized solar cell, we don't have efficiency up to 10 also, right? Still it is in the research mode. Okay, right. Whatever I'm talking about is a conventional silicon solar cells. It's 20%. Okay. So this is another research we can do. Okay, and self-cleaning paints. Okay, right. What happens when you coat your right? You might have observed, okay, they are available in the market. Okay, you can coat the exteriors of your houses and all with the self cleaning paints. When water falls, okay, it rolls down. Okay, we are mimicking the lotus. Okay, we call it as lotus effect. Okay, so lotus have got papillae, very small hair-like structures. They are coated with wax. Okay, similar to that, what we do is we use nanomaterials. Okay, they are coated with polystyrene or any hydrophobic materials. Okay, on the surface, so that we can develop super hydrophobic coatings on clothes. Okay, self-cleaning clothes. Okay, during rain, no droplet of water will adhere to your this one that cloth. Okay, so there are various methods. Okay, zinc oxide preparation is very simple. Okay, you can take waste battery and put it in nitric acid. Okay, and add small amount of urea and burn it to 400 degrees Celsius. Self ignition of urea will convert zinc nitrate into zinc oxide. Okay, zinc oxide nanoparticles can be easily prepared, and you get up to 20 to 30 nanometer nanoparticles. Okay, even if you don't have to go for XRD, I can tell you 100%. Most of just you have to burn it in terms of air, right? So just polystyrene is also available, your thermocol and all. You just put it in toluene or acetone, it will dissolve, and add this zinc oxide nanoparticle you prepared in that, and you mix it and paint it. Okay, it's your super hydrophobic coating. Okay, so that's the same technology. I'm just giving you a vague idea about this. And we know, I say gold is not yellow anymore now. Okay, gold is not yellow anymore. Gold nanoparticles, okay, have different colors because of confinement effect. Okay, electron confinement. Because when you confine electrons, the color changes. Okay, I'm wearing the blue color dress. Okay, I like blue color, but my dress doesn't like blue color. It reflects all the blue color. Okay, so if I control the electrons, okay, if I confine the electrons, it may look red, right? The same dress I can wear. Okay, I can change the nanoparticle size of gold. Okay, I'll get different color dress. Okay, that's the next generation nanotechnology. Okay, Swarna Bindu is another, in Indian Ayurveda, people were using Swarna Bindu Prashana. Swarna Bindu is gold nanoparticles. You can see the color of that gold nanoparticles is pink. Okay, we administer it to children. Okay, just to increase the immunity. Okay, now when it comes to environment, the agriculture. Okay, so what are the challenges in agriculture? Okay, so low crop yields, water scarcity, inefficient irrigation, pests, diseases, soil degradation, poor soil fertility, excessive use of chemical fertilizers. We are polluting our environment. Okay, so when I say environment, so I'm just taking some examples here. Okay, so the problem is there are many things are happening. The climate change is happening, environmental stress is there, lack of access to resources, small scale farmers. Okay, there are so many problems in agriculture. Okay, so nanotechnology solution for the challenges. Okay, we can go for nano coatings for fertilizers. Conventional fertilizers often result in nutrient leaching, meaning nutrients are lost to the environment. Okay, nanotechnology can help produce controlled release fertilizers with nano coatings, which gradually release the nutrients, controlled release or sustained released, fertilizers. This ensures that plant absorb nutrients more efficiently, resulting in better crop growth, higher yields. For instance, nano silica coated fertilizer can enhance nutrient uptake by plants. What happens, how plants absorb the nutrients? The roots, they basically absorb the nutrients in conventional thing. But if you use nano fertilizers, for example, what is the per acre, you have to put like 50 kg or 1 quintal of urea. But if you use nanotechnology, nanomaterials, you have to use 500 ml nanomaterials. Just spray it. Wherever you spray it, it will absorb. Okay. Only thing you have to cover with your the PPE kit. Okay, because it should not fall on you. Because nanomaterials are so small, they can enter into your skin also. Okay. So the plant, even it can cross the guard cells of the plant, and it can enter. So nutrition, plant doesn't have to take nutrition from the root. Even if you spray it on a stem, it will absorb. So you require just half a liter of the nutrient that is fertilized, not in kgs. Because what happens when you put that much of fertilizer, eutrophication takes place. All the nutrients go and they are collected in the river or something. Right, because of nitrogen increase in the nitrogen content and then nitric oxide or something, nitrate content. Okay, blue baby syndrome or so many other problems starts. Okay, right. So advantage is just you require a small amount of the fertilizer. Nano fertilizers. Okay, it's a IFCO company has developed already. Then nano fertilizers. Okay, in Kenya, nanotechnology has been applied to improve the soil quality. Nano encapsulation, encapsulated fertilizers slowly releasing nutrients to crops, enhanced crop yields by 30%. This increased food production contributed to the food security and improved income for local farmers, addressing both hunger and poverty. Okay, so soil nutrient analysis with if the soil requires nutrient, then only you add, otherwise not required. Right? So nano fertilizers. Okay, smart irrigation systems. Okay, nano hydrogels. Okay, nanotechnology has enabled the development of nanohydrogels that absorb large amount of water and release it gradually into the soil. Okay, this helps maintain soil moisture, ensure plants have a steady water supply, reducing the need for frequent irrigation. Okay, so there is an example of cellulose-based hydrogels for agriculture. Okay, sensors for moisture monitoring. Okay, nanotechnology-based sensors. Okay, soil moisture sensors, nano-based sensors can be embedded in the soil to monitor moisture levels in real time. These sensors can relay data to farmers, allowing them to irrigate only when it is necessary, ensuring more efficient water use. This technology helps in precision agriculture, optimizing irrigation, and conserving water. Okay, so in agriculture,
Excuse me,
we are
sir.
using this. Sir,
Sir,
sir, can you hear me?
sir, you
Yeah.
are not audible, sir.
Now, am I audible now?
You are not audible.
Now, hello. Now, sir, hello. Am I audible? Am I audible?
Yes, sir, you are audible.
Yes.
Audible, sir.
Okay.
Yes, sir, you are audible. Sir.
Yeah. So in another technique we use in pesticides, we use pesticides, okay, which harm the environment. Pesticides, people say we should not use, and we should go for what like organic farming and all. Of course, organic farming is important, but what happens, organic farming, the yield will not be there, and that's a problem with the farmers. So, and we have to protect the environment. At the same time, we should not use too much the fertilizers and pesticides. So nano pesticides, what I mean by nano pesticide? Okay, what we do in this case, okay, we prepare nano carrier, a box kind of thing. Okay, nano carrier, you can see here, nano carrier. Okay, and to kill that, you have to encapsulate that pesticide is encapsulated with nano carrier, and we lure the pests. Okay, what do you call that? Semiochemicals. Okay, semiochemical means like pheromones. They attract oppositely, right? Opposite gender. This one. Okay, the pests. Okay, when they are lured. Okay, inside there is a pesticide, and it kills the pests. Okay, this minimizes the amount of pesticide required to reduce the environmental impact. Okay, so just half liter or something is sufficient. Okay, this nano pesticides and encapsulated pesticides for 1 acre land. Okay, you don't require very high this one. Okay, very small amount. Okay, half liter or quarter liter is also okay. 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 So nano enhances soil fertility. Okay, environment. Okay, in Arab countries, The problem is they don't have the right soil to grow. Okay, it's totally silica. Okay, it is all desert. What they have done, in Dubai and all, they have started using nanocarbon materials. Nanomaterials such as nanocarbon can be added to soil to improve its structure, increase water retention, and promote the growth of beneficial soil microorganisms. Okay, nanocarbon as fertilizer. Okay, nanoclays are also used. Okay, nanoclays which help to improve the water holding capacity of the soil. Okay, water holding capacity is because of clays. Okay, so we use nanoclays prevent. Okay, right, preventing the drying out of the soil. Okay, so this has been already implemented. Okay, soil remediation. Okay, nano remediation, we say contaminated soil. Okay, usually we use iron nanoparticles which are environmental friendly because in soil iron is already there. Okay, you can see red soil or something, so iron is already there, are used for remediation of contaminated soils, particularly for soils polluted with heavy metals like lead, arsenic, cadmium. These nanoparticles help breakdown. Okay, they will not help breakdown of these inorganic materials, but they will immobilize the toxic substances. These toxic substances will adsorb on the surface. Okay, you can remove them. Okay, so either nanoparticles in contact, either they degrade the contaminant or sequester or what immobilize the contaminant. Okay, adsorption takes place. Okay, it makes the agriculture safer. Okay, toxic chemicals you have removed. Okay, nanomaterials are also used in packing. Okay, nano silver particles and other microbial agents are being incorporated into food packaging, antimicrobial agents. Okay, silver is antimicrobial agent. Okay, packaging materials to prevent spoilage and contamination. This type of packaging can extend the life of fresh produce like fruits, vegetables, reducing waste. For example, nano silver films have been shown to inhibit bacterial growth, keeping the food safe for longer. Okay, these nanofilms are, I mean, we are using some, even what do you call your Kaju Katli and all, and still they're using nanofilms, okay, of thin films, not nanofilms. The silver films are they're using, but nano definitely, I mean, a very small amount it is. Okay, nano silver is used in your washing machines nowadays. That's the reason silver prices have gone like anything now, 2 lakh rupees, something like that per kg. So, right, SDGs, okay. Um, we can address using nanotechnology, zero hunger, okay, enhances crop yields through improved fertilizers and pest control, reduces waste and increases food security, clean water and sanitation, okay, improves water efficiency and quality using nanotechnology in irrigation and water filtration systems. And SDG 12 talks about responsible consumption and production, minimizes resource waste, okay, optimizes inputs like water, fertilizers, and pesticides. Okay, SDG 13 talks about climate action. Okay, definitely, right, reduces carbon footprint because you are using small amount of pesticides, small amount of these things. Okay, SDG 15 talks about life on land, promoting biodiversity and soil health because healthy soil is crucial for agriculture, and nanomaterials, nanotechnology help to restore and maintain soil health while promoting biodiversity because you are not using in right large amount of bulk. Okay, so in conclusion, nanotechnology offers solution to variety of pressing agriculture needs. Okay, from improving crop yields, water use efficiency, reducing pesticides reliance, enhancing food security through right examples like nano encapsulated fertilizers, smart irrigation systems, and nanosensors for disease detection. Nanotechnology is providing farmers with tools to meet demanding demands of a growing global population while promoting environmental sustainability. However, as with new technology, careful regulations because nanomaterials we cannot say it's safe as it is now, because what happens, nanoparticles can, I told you, can cross blood-brain barrier and all. Okay, so we have to handle this with care. Okay, so nanotechnology, right, we use in turmeric. Nowadays, people are talking about nano turmeric. Okay, all right, we add, if you make it alkaline turmeric, it turns to red. Okay, in earlier days, okay, we were applying the kumkuma that's basically made up of turmeric. Okay, so our body takes the alkaline things. That was the reason, okay, why we convert that turmeric into red turmeric. Okay, so when you talk about nanotechnology, you can make nano kumkumas, okay, which help in easy absorption of the curcumin, which is the main ingredient of turmeric. Okay, so environment we talk about, when we talk about environment, it's drinking water also comes. Okay, water is an important component of our life. It would make sense that the quality of the water should be just as important as the quantity. Drinking water should be clean and free from toxic contaminants. Nowadays, all the resources are contaminated with hazardous compounds. You might have seen in Bangalore that Vrishabhavati river, it has become a drainage. Okay, so water is totally contaminated. Industrial effluents are the main sources of contaminants. Okay, the industries, they don't treat properly, right? They release it. Okay, if you don't treat it properly, then water goes into the environment. Of course, it has got self-cleaning property, but it's very difficult to remove the toxic compounds. Okay, entry of pesticides into bodies. Okay, environment, we are putting a lot of pesticides and all. Of course, nanotechnology, we have reduced it. Okay, the use of pesticides, but still they enter into the environment. When it rains, all the water that pesticides go into the contaminate the groundwater. During the rain, they are collected in the rivers. Okay, contaminating river water also, right? So pesticides are there in the environment, and we drink every day some ppm of pesticides. It is the reality. We are drinking little amount of pesticides. Okay, so pharmaceuticals. If you go to doctor, he will give prescribe whatever the disease it may be. He will give you the some fluoxetines, norfloxacin, ciprofloxacin, or something, sulfa drugs or tetracyclines or whatever it is. Okay, so different types of antibiotics we take. Okay, so all our water bodies are contaminated with even pharmaceuticals, antibiotics. Okay, what happened? We call them as emerging contaminants. Emerging contaminants, we don't monitor them. Okay, there is a perceived or real threat to human health or environment is there. A lack of published health standards or an evolving standard. A contaminant may be emerging because the discovery of the new source or new pathway to human, a new detection method, right? So it is called emerging contaminant. So, right, I'm just talking about one. There are also many, right? Pesticides are there, pharmaceuticals are there, plasticizers are, fragrances are there, lotions are there, shampoos are there, flame retardants. We don't know. Every day we apply shampoo, right? Where it goes? It goes to domestic sewage and it contaminates our finally the river water or the groundwater, right? So it is there. We use detergents, we use sunscreens, we use cosmetics. So we are contaminating the environment. Okay, these are called emerging contaminants. Okay, how much antibiotics we use? There is a estimation by one Buchel in 2010. Okay, right. He published in 2015. Okay, he told 1 lakh tons of antibiotics we use. 1 lakh tons. Okay, worldwide. In it is 15 years back. Now it may be after Corona, it may be 2 or 3 tons, lakh tons. Okay, that much pollutant. Okay, that much antibiotics we are using. Okay, so how these pharmaceutical enter the environment? Okay, we use human use, veterinary. Okay, even right, animals like cows, right? All these we give injections. Okay, hospital waste. Okay, effluent from industry. Everything goes and contaminates the ground and surface water. When I take an antibiotic, it will not be digested in our body because it is antibiotic. It is not probiotic. It is antibiotic. Okay. So it kills the bacteria. It doesn't know good bacteria or bad bacteria. It kills all the bacteria. Okay. So basically 20% of the antibiotic dose is used to kill the bacteria. 80% goes through our excretion. Where it goes? The sewage water, to the sewage water. And when it rains, everything goes to river water. Okay, river water is contaminated. So what happens? See, these bacteria, so these antibiotics are there in water, and bacteria present already in the water, they start eating these antibiotics. Okay, if you give small amount of antibiotic, it's a poison. Actually, antibiotic is a small poison. If you use small amount of poison every day to the bacteria, it develops antibacterial resistance. Okay, and you remember Chanakya used to give poison to the young children, okay, girls, okay, which kanyas used to make. Okay, afterwards, okay, it develops antibacterial resistance, anti-poison resistance. Okay, so the bacteria will not be killed anymore with the same drug, right? So that's the problem. Okay, so how to remove this? Okay, what municipal water treatment plants do? Aeration, flocculation, filtration, and disinfection. Aeration, okay, it's a fountain kind of thing. It removes the odor, okay, when it's sprayed, okay, and so because in sunlight and air, okay, it removes the odor. Flocculation, we add potash alum or something to remove the colloidal particles. Filtration, to remove the suspended materials. Finally, disinfection is the only chemical procedure we do. We add what? Chlorine or something. It's a chlorine is the most common disinfectant. Okay, chlorine, when we use chlorine, okay, so all the bacteria die. It's basically the disinfection process. There is membrane filtration technique is there. Okay, membrane market is also huge. Okay, so we use like RO, reverse osmosis. Okay, different membranes. Okay, we use like microfiltration membranes, which are used in your ACs and all filters, AC filters, microfiltration. Okay, ultrafiltration, we use it in water purifiers. Okay, nanofiltration also we can use it in water. Right, some hi-fi labs we use nanofiltration membranes, like biological safety laboratories. Okay, right. So we use the filters made up of a nanofiltration membrane. And water we use like RO membranes also we use. Okay, so to treat the water. Okay, and then people are talking about mineral water and all. You know this lady. Okay, all right. So mineral water, she was right. You can see that Aqua di Cristallo Tributo Modigliani, okay, which costs around 40 lakh rupees. Okay, for 1 liter of bottle. It's made up of gold coated this one, right? So that can be made, okay. And if you people are, fed of because of what you call that alkaline water, which costs 60 bottles. Right, per bottle cost to around 58 rupees, but actually they add calcium bicarbonate, magnesium bicarbonate, and potassium bicarbonate and make alkaline just to maintain the pH 7.5 to 8.5. So we call them as alkaline water. You don't have to pay that much of 58 rupees. You can add a pinch of this mixture. So normal water, it becomes alkaline water. Okay, because of my research in water related things. Okay, I was invited by Chief Minister Meghalaya and Water Resources Minister Medbay Langdo, okay, to solve some problems of Meghalaya. This one, okay, basin right, water research this one, okay, for right. So I received Young Scientist Award, okay, some best paper award in nanotechnology. So nanotechnology environment, we talk about air pollution is also another problem. Okay, air purification using nanocrystals. Okay, photocatalytic materials. Okay, semiconducting materials. Okay, what happens? When you use nano, right? So how to degrade a compound, organic compound? We just burn it. Okay. Instead of burning, we use nanotechnology. What we do, we convert that organic compound into carbon dioxide and water using nanotechnology. This is called photocatalytic process. What we do, we use the UV light, or the sunlight also can be used. Okay, we excite, okay, which the light excites electron from valence band to conduction band. Okay, the hole is created in the valence band. It takes electron from water, forming OH radicals. Okay, OH radicals are, once OH radicals are formed, they are called environmental detergents. Okay, OH radicals are formed because of sunlight hitting the water droplets or the moisture present in the air. Okay, so that OH radical, okay, will degrade all the organic matter. All the volatile organic matter is degraded by OH radical. That's the reason we call the OH radical as environmental detergent. Okay, some molecules will not react with OH radicals, which have got really long lifetime in the environment. They are, we call them as CFCs, chlorofluorocarbons. Okay, you might have heard about it. Okay, they go to lower stratosphere. Lower stratosphere, we have ozone layer. Okay, when sunlight strikes, okay, ozone layer, it has got its dynamic balance. Okay, equilibrium. What happens? Right, ozone O3 is there. Okay, it splits into O singlet D and oxygen radical. Okay, and it recombines and forms again ozone. That's the dynamic equilibrium. But when this CFC goes there, okay, it forms chlorine radical. And this chlorine radicals take that oxygen, which is formed by oxygen radical, which is formed by splitting of ozone because of sunlight. Okay, sunlight, because the UV radiations are absorbed by ozone, right? So, but what happens when this CFC goes there? They also split and they react with the ozone reacting with giving oxygen and O singlet D. O singlet D is reacting with chlorine, and for it's a chain reaction. So ozone becomes oxygen. Ozone becomes oxygen. Oxygen is required in the troposphere, not in the stratosphere. Stratosphere, we want ozone. Okay, so that leads to ozone depletion and all. Right, I'm just telling you about, right. So the OH radicals are called environmental detergents. Only few molecules will not react. That's the reason they are banned now. Okay, in catalytic converters, we use photocatalytic UV technology. Involves activation of catalytic particles in a medium to attract airborne particles. Nanotechnology is currently in use for purposes of filtering air. Involves a process known as photocatalytic oxidation. Okay. The catalyst used commonly are, titanium oxide and zinc oxide. Okay. So UV light, right, when they are exposed to UV light, they, right, basically they have got band gap of 388 nanometers. Okay, UV air radiation is sufficient to excite an electron from valence band to conduction band. Okay, so that excited electron, which is in the conduction band, it also forms superoxide anion, and finally it forms hydroxyl radicals. Okay, these hydroxyl radicals react with all volatile organic compounds and other pollutants, degrading them to carbon dioxide and water and ammonia and all those things, kind of these kind of small molecules. They break down the big molecules into smaller ones. See, various porous oxides coated with the catalytic nanoparticles are being explored for use in removing sulfur dioxide and other contaminants. So this is the technology. Photocatalysis, what we do in air purification. Polluted air comes front filters, okay, like microfiltration membrane or something. Then high performance filter or electrostatic dust collection. Okay, then we have photocatalytic filter and UV light sources there, just to kill the just to excite the electrons from valence band to conduction band. And when what happens when OH radicals are formed, okay, they degrade all the organic matter. Even it will kill the bacteria. Okay, when you excite an semiconductor, hole is created, and hole requires an electron. It may take electron from the bacteria also. So bacteria will be killed. Okay, you are not burning it, but you are killing it using UV light. Okay, and nanomaterials. Okay, semiconducting nanomaterials. The band gap of TiO2 is 3.2 electron volts. Okay, which lies in 388 nanometers, near visible. Okay, ultraviolet. Okay, UVA. Functional filter is there. Okay, induced fan. Okay, clean air comes out. So this is the working principle of nanophotovoltaic catalytic air purifier. Okay, so this is another technique. Okay, how it works. Water treatment, we use nanofiltration, catalytic degradation of water pollutants, adsorption of pollutants, magnetic nanoparticles are also used, nanosensors are also used. How we prepare nanomaterials? There are two approaches, top-down approach, bottom approach. Okay, so top-down, we use ball milling or lithography. Okay, bottom up, we use sol gel procedure, chemical vapor deposition. Okay, inert gas condensation. Okay, so they're all bottom approach. Okay, bulk material can be broken down into fragments, then nanomaterials, nanoscale structures. Or you can go other way around, atoms, you make ions and they make clusters, and then nanomaterials. This is top down and this is bottom approach. Okay, so which is better? So both are important, but basically pure nanomaterials, you get it from bottom approach. Okay, you can control the particle size and all, because when you hammer, for example, you take a glass, okay, glass, this one piece, and you hit with the hammer, okay, it breaks. The particle size will not be the same. Okay, so top-down approach, you produce large quantity of nanoparticles, but it is difficult to achieve same size nanoparticles. Similarly, from atoms to clusters to nanoparticles, you can get, high, right, uniform nanoparticles, but the right, you cannot produce in large scale. Okay, there is a you have to make some compromise. Okay, some trade-off is there. Solution combustion technique is the easiest method. We can produce nanomaterial. Okay, just zinc oxide. For example, I'll give an example. Zinc nitrate, you take metal nitrates. Okay, right. Add some urea. Okay, or any fuel. Okay, and heat it to a temperature where the self-burning, self-ignition of that fuel occurs, and that leads to formation of nanomaterials. It's a solution combustion method. Okay, the right, how you check it, it's very difficult to see the nanoparticles because you cannot see it. Okay, we can see the optimum range, right, whatever visible range is 400 to 750 nanometers or so. Okay, below 400 we cannot see. Below violet, it is ultraviolet, we cannot see. Higher energy, right, and above red, infrared, we cannot see. Okay, right, below violet. Okay, so what happens, if it is the size, for example, size of nanomaterial is 250 nanometers. Okay, so which is half of your green light, green around 500 nanometers. So half of that is 250. So still we can see sometimes, some reflections may come. Okay, see, this is the particle and the wavelength of light. Okay, if the light is not hitting the particle, we cannot see it. It becomes invisible. There may be n number of nanomaterials in between me and my screen, but I cannot see them because the light, okay, it has got a wavelength and it will not hit that particle, and the other side I can see. This is how it works. Okay, if it hits the particle, I can see the particle because it reflects, but whatever we see is because of the reflection. Okay, so nanoparticles, no optical microscope helps you to characterize nanomaterials. You require electron microscope only. Okay, scanning electron microscope or transmission electron microscope. Of course, you can use probe microscopes. Okay, all right. What do you call STM and all? Okay, AFM, force microscopy. So graphene is the one of the hardest material. Okay, which was developed accidentally actually. Right, Jain. Okay, he got Nobel Prize Okay, so if you take a sellotape and you take a pencil and just rip it off, it's called exfoliation. You get some what nanomaterials like graphene is okay. You collected some graphene. Though it's in micro scale. Okay, if you have to repeat it thousands of times or crores of times, then you get small amount of graphene. It's a physical method. So chemical method, you can just go for right electrochemical, right electrochemical exfoliation. We say to take two graphite rods and pass electricity. You know oxidation takes place at right anode and reduction takes place at cathode. Okay, so the sulfur SO4 ions, SO4 minus 2 ions have same or similar size as the spacing, despacing in graphite. So it will exfoliate, it will enter and exfoliate the graphite layers. Okay, single graphite layer is called graphene, which is the hardest material, one of the hardest materials. Okay. Some studies have proposed that the decomposition of SO2 minus SO4 minus 2 during the exfoliation generates various gases that produce such as SO2, O2, and hydrogen gas, which drives the expansion of the graphite interlayer spacing. Okay, the mechanism is not 100%, but this is the way how we prepare, right? Graphene nanoparticles, graphene. Okay. So another like transmission electron microscope is used basically to check how the right topography of that material. Simple method, sol gel method is also there to prepare nanomaterials. Okay, sol, that solid dispersed in liquid is called sol. Liquid dispersed in solid is called gel. Okay, so in sol gel, metal alkoxides or inorganic salts are used. Okay, it involves hydrolysis and partial condensation, forming metal oxides. Okay, I'm not going in detail about this. Okay, if there is pores in between this air pockets are there in the gel, we call it as aerogel. Okay, if the air pockets are not there in the gel, so it's called zero gel. Okay, if you remove like supercritical drying, okay, leads to air pockets. Immediately you pass some gas and remove the solvent. So what you get? You get porous gel. Okay, gel structure is like this. Okay, the bottom one, gel structure. You remove the water, you get air pockets. Okay, then it's called aerogel. Okay, if you remove, allow it to evaporate, thermal evaporation of this gel, what happens? The pores shrink and you get zero gel. Thermal evaporation leads to shrinking of pores and no air pockets will be there in that gel. It's called zero gel. Okay, symbolic schematic representation of this process. Chemical vapor deposition technique is a chemical process used to produce high purity, high performance solid materials. The process is often used in the semiconductor industry to produce thin films. In a typical CVD, a wafer substrate is exposed to one or more volatile precursors, which react on the substrate surface to produce the desired deposit. Okay, frequently volatile byproducts are also produced, which are removed by gas flow through the reaction chamber. Okay, so polycrystalline silicon is deposited from silane using the following technique. Okay, SiH4, when you heat it to 1100 degrees Celsius, you get silicon, and hydrogen gas comes out. So this is the method. Okay, so usually the substrate is in the cold stage. Okay, silicon nitride is often used as an insulator and a chemical barrier in the manufacturing of ICs. The following two reactions, okay, basically SiH4 plus ammonia reaction use Si3N4, okay, silicon nitride, or SiCl2H2, okay, dichlorosilane, okay, reaction with ammonia. It's chemical vapor deposition. Reaction happens here. Okay, that's the difference in physical and chemical vapor deposition techniques. Okay, then Si3N4, right here, HCl and other gases, they come out. Finally, I thank all my collaborators. The first person is Dr. Anagadkar. Okay, he has done PhD in 2016 under my guidance. Dr. Maladi, he has done PhD in 2017. Dr. Bamre has done PhD in 2019. Arshit Kulkarni, Dr. Arshit Kulkarni is a mechanical professor. Okay, has done PhD in 2021. Webo Chate and Professor Pooja. Okay, he's from computer science. He's from civil. He's from mechanical engineering. This is Professor Peters from University of Leuven. He was my professor during my postdoc in Belgium. My collaborator, Bart Dils, another collaborator from Spain, Eduardo, my professor, my friend Sean Call, Yunji Shu, my professor at University of Alberta, Canada, and my collaborator, Yunus Shakur from Malaysia, my guide, Professor Nanjibur, my collaborator and our earlier principal, Dr. Deshpande, and Dr. Chate, my collaborator, Dr. Kulkarni, my collaborator, Dr. Shetty, and Professor Amin Bhavi, sir, my mentor. So thank you all. You can contact me, my email, and my mobile number is 7019572324. You can call me also. Right. If you have any questions, please, I'd be happy to discuss.
Definitely, sir. Indeed, a very good presentation, sir. Thank you so much.
Thank you, sir.
Dear participants, if you have any questions, please post. Sir, we usually hear that in the national news that the residues of the waste that remains in the farmland, they are usually burnt. In Haryana and all, it is usually we hear that. And because of the burning, it causes lots of pollution.
Ash
And
this one, right? Huh?
so,
Yeah.
what is the remedy for that, sir?
Okay,
In
that is
using nanoparticles.
okay. Usually, what after cutting of the this one, right?
Yes.
They burn it in as well, right? That is you in large this one you cannot do anything, right? This one, okay, we cannot do any nanotechnology for that open combustion things. When you burn this one open air, so that gases will come out definitely. So that what we can do is we can after cutting we can just use nanotechnology to dissolve those things or treat them. Okay, using bioactive materials, we can just treat them. We convert into fertilizer and use it. That's another thing we can do instead of burning it. There are
True, sir.
procedures. Okay, biotechnology people will help you to right. We can make bio materials which will help definitely to degrade the materials, and we can use them as a fertilizer. Composting and all we can do in
Yes.
large scale. Yes. Instead of burning. If you burn it, we cannot we cannot remove it easily.
Yes.
They will settle. Yeah.
True, sir. You have touched upon everything, sir. As per your title, the
I tried
semiconductor
my best,
related,
sir. Yeah,
environment
environment
related
I
also.
tried, sir. Yeah, yeah.
True, sir, true. To all the dear participants, Raviraj sir is in Chennai attending one conference. So busy that, but sir, we requested Raviraj sir, somehow you come. And therefore, I hope you might have noticed Ravraj sir session was in the last, but because he has to attend another event at during that time, so we shifted it to 2 o'clock.
Thank you, sir.
And now the person who is doing earlier at 2 o'clock, he will be joining. Dr. Arun Nisim Gaudar will be joining at 5 o'clock, sir.
Any questions? I will be.
Yes, participants. Yes, sir. Sir, on behalf of all the participants, I wholeheartedly thank you for your gracious presence.
Thank you, sir.
And as per the topic, as I said, entire thing you have delivered, though the time is very short, but you covered almost everything, sir. So on behalf of participants and on behalf of KLS management also, thank you. And on behalf of all my colleagues, especially from my behalf of my principal, Dr. V. Kulkarni sir, and on behalf of all the organizing committee, I hope this coordination and support we will keep receiving from you, sir, in future also for all our
My pleasure,
events.
sir.
Yes, sir. Yes, sir. Thank you so much, sir. Thank you, sir.
Thank
Yes, sir.
thank you, sir. Thank you.
Yes, sir. Thank you.
Okay, sir. Thank
Yes.
you, sir. I'll just leave this one, sir.
Yes, sir. Our next speaker will also be there, sir, in the session.
Yeah, yeah,
Yes, sir.
yeah. I'm
Yes.
exiting. Yes,
Then,
yes.
thank you, sir. Thank you very
Thank you,
much.
sir. Thank you, sir. Thank you.
Okay, okay, thank you. Dear participants, the next session will begin exactly. The next session will begin exactly the scheduled time. 3:30 begins at 3:30. We have 6 minutes. Sannaikar sir, there is very much
Yes,
echo
yes,
there. Very much
yes,
echo
sir.
there.
Okay, sir. Yes, sir. Sir, is it audible now?
Sir, audible, sir. ನಿಮ್ ಪಿಪಿಟಿ ಕಾಣ್ಲಿಕ್ತಿಲ್ಲ ಇಲ್ಲಿ ಈಗ ಕಾಣಿಸ್ವಲ್ತ ಆಗ ಕಾಣ್ಲಿಕ್ಕಿತ್ತ ಬಯೋ ನ್ಯಾನೋ ಇಂಟರ್ಫೇಸಸ್ ಅಂತ ಬರ್ತಿ ಈಗ ಮತ್ತೆ ಹೋತು Yes, sir, your PPT is visible now. Sir, can you start now? Subramanya, sir. Hello. So, dear participants, I welcome you all for the next session. And as you can see on the screen, the next session will be on bio-nano interfaces. And the session expert for this particular topic is Dr. M.S. Sarnaikar, Assistant Professor in the Department of Physics at KLSVDIT, Haliyal. He is also one of the program coordinators of this ATAL FDP. And it gives me immense pleasure to introduce my friend, Dr. M.S. Sarnaikar. He is an academician and a researcher in the field of physics. Dr. Sarnaikar completed his MSc in physics from Karnataka University, Dharwad in the year 2012 and subsequently earned PhD in the year 2019 under the esteemed guidance of Professor Sanjeev R. Inamdar Sir, Department of Physics, Karnataka University, Dharwad. Dr. Sarnaikar has an impressive research portfolio, having published more than 25 research articles in reputed international journals. His primary areas of expertise include fluorescence spectroscopy studies of nanoparticles and biomolecules, as well as theoretical studies such as density functional theory and molecular docking investigations. He has been actively involved in the scientific community as a former member of SPIE Photonics and the Indian Science Congress Association. His contributions and potential were recognized early in his career when he received an international travel grant for young scientists in the year 2018, enabling him to participate in overseas scientific events. Dr. Sarnaikar has also presented his research at numerous national and international conferences, workshops, and scientific meetings, gaining wide appreciation for the depth and quality of his work. With these brief words, I now present before you. I now request Dr. M.S. Sarnaikar, sir, to go ahead with his presentations. Sir. Hello. Sir, you are not audible, sir. Hello, participants. Are you listening?
Yes, sir.
Sir, now speak, sir. Sir, your presentation is moving, changing, but I will check my case, sir. Dear participants, can anyone please just type a message because we are not listening? Does anyone is hearing what is being said? Sir, am I audible to you?
Yes, sir. Your sound is clearly audible, sir.
Which my sound is, and what about the speaker?
No, sir.
Speaker, yes, sir, yes, sir. That is the problem. Yes, sir. No, sir, no.
Hello.
Now you are audible, sir. Go
Yes,
ahead.
thank you, sir. Thank you so much,
Yes,
sir.
yes, sir. Thank you. Sir, your
Uh,
PPT should be made slideshow like.
Yes, sir. Yes, sir. Yes, sir.
Okay. Share PPT, sir.
Yes, sir.
Okay, sir. Great, sir. Great.
Is it now, sir? Fine.
Yes, sir. Go ahead, sir. Go ahead.
Thank you so much, and very sorry for the interruptions happened. Now, this is what the outline of my presentation. It goes like this. Here, I would like to throw some light on nanoparticles introduction, as this topic is already covered by the so many speakers in the previous sessions. And now, In the second part of that, I would like to discuss about nanomaterials, how they are useful in biological fields then. In the third part, I would like to cover what are the different techniques which are available for nano interfacing, because if I want to tag a biomolecule with a nanoparticle, I must have some different techniques. So we will discuss about what are the different techniques we have in bio-nano interfacing. Then if the tagging takes place, biomolecule and plus nanoparticle attaches to each other, well, how to confirm that one, whether there is a successful interaction between the biomolecule and nano interactions or not. In order to confirm that one, we have a different experimental techniques that I will discuss in the upcoming slides. So particularly in the next few slides, after completing the experimental techniques, I will go to the particular examples which I have studied in my experiments. I would like to discuss about the two proteins. One is bovine serum albumin and another one is a human serum albumin. There is an interaction between these biomolecules with one of the heavy metal free quantum dots, that is indium phosphide zinc sulfide, then quantum dots. At the third part, even I would like to discuss about the interactions between trypsin from the bovine pancreas and fumarine 440 dye. Later, we will discuss about the summaries and inferences and what are the future challenges and scopes also we'll discuss. So finally, well, let us begin what exactly the nanotechnology means then. So I think the participants already, it is very clear for you people that since 5 days we are discussing about nanomaterials and nanotechnology. And in the previous session was it is completely environmental. There also we have seen what exactly the nanotechnology means. See, ultimately, nanotechnology is the science of manipulating the atoms and molecules to make them very advanced nanomaterials. So we all know what exactly the molecule is, atom is, and all. So this is the very fundamental things which are very much essential in order to understand the future things, what we have done in our research work. Well, so nanotechnology is the understanding and manipulation of a matter in sizes ranging from approximately 1 to 100 nanometers, where unique phenomena will enables us to go to the new applications. So then what are the reasons the nanoparticle has a different special unique properties? So there are certain various reasons why the particles or nanomaterials have a different special unique properties, uh, but not their counterparts have. So because of, I think in the previous discussion, it was very clear that how by decreasing the size of the materials from bulk material to the nanoscale, what happens to the surface volume ratio. So the surface volume ratio is the most important parameter here that what gives the unique properties for the nanomaterials. See, in the graph it is mentioned here, whenever the size of the material is decreased, you can observe surface to volume ratio is increasing. So because it is detailed, in detail it is explained here, the larger the sample, the smaller the fraction of atoms on the surface, and atoms on the surface have fewer neighbors than atoms inside. So the thing is, as we decrease the size of the materials from bulk materials to microscopic scale and then to nanometers particle size, 100 nanometer, 20 nanometer, like that, their surface to volume ratio will obviously increases, and which is very much essential for the unique properties of nanomaterials. The another reason why the nanomaterial have different properties, very advantageous properties, which are very helpful for our applications then, because of the size effect. This is all we already know, quantum confinement effect then. Particle sizes approach to the characteristics length of for the material. At the nanometer scale, properties become dependent on size. What are the properties which are depending on this size at the nanometer scale then? See, whenever you go discuss about the bulk materials, the properties which I have quoted here, like chemical properties, thermal properties, mechanical properties, optical properties, electrical properties, magnetic properties, more or less, they are almost remain same at the bulk size then. But when I go to the nanometer scale, the chemical properties like the reactivity, catalysis, properties will change, as well as the thermal properties. For example, if I take the gold in the bulk material, that is what is the melting temperature of the gold, or what is the melting temperature of the iron, copper in the bulk size. If I decrease the size of the those materials, what happens to the melting temperature? Obviously, it changes. So like that, mechanical properties here also, the adhesive property, this is most important. Here, what happens? The adhesive property of bulk material with the another is somewhat almost constant at the bulk scale. But when you go to the nanometer scale, the adhesive property will definitely change. That impacts on the usage of nanometer, nanoscale materials. Even the capillary forces will also change. So like that, one more important category where these optical, the nanometers materials will play a major role is optical properties. Absorption properties of the nanomaterials will change. Scattering of the light will change. So their fluorescence properties will be different as compared to the bulk material and nanoscales. And the electrical properties, tunneling current. So as we go to the lower size, the tunneling properties will play a major role. Magnetic properties will also change. That is, so a super magnetic effect will takes place. So with the help of by knowing all these six properties, these six properties are different for the bulk material as and for the nanoscale materials. Here, this graph shows that for particularly it is taken for the gold nanoparticles. One property is taken here. The thermal property is taken. If I take the gold nanoparticles, if their size is somewhat around 200 nanometer or something like that, uh, the melting temperature is little bit high. As we reduce to the nanometer scale, 50 nanometer and something like that, the melting temperature goes down. So this also shows the major role of size effects on the nanoscale properties. Here it is clearly mentioned that melting point is a temperature at which the atoms in substance have sufficient energy to overcome the interatomic forces that hold them in a fixed position in a solid. On a scale of macroscopic length, the melting point material does not depend on the size. Both the ice cube and the glacier melt at the same temperature. So this is what at bulk levels, there is no difference in the melting points of a bulk materials, even if it is a 2-meter sized, 2-meter cube sized ice cube, or if it is a 1-meter cube sized ice cube, there is no much difference in the melting temperature of both the materials. It is all because of the surface effects then. Even heat transfer in materials is carried out by two different mechanisms. Lattice vibrations, that is by phonons, and because of free electrons movement then. The size effects will definitely affect these two properties, and it will be observed when the particle size becomes close to the phonon or electron free path. Here, this slide shows how the quantum confinement effect changes or affects the band gap of the materials. So as you can see here, clearly it is depicted that for the bulk semiconducting materials, there are energy levels there which are almost continuous, so valence band and conduction band. But as you go to the size, when we reduce the size of the nano materials to the nanoscales, this is for one material where the energy levels are now they started to separate even in the valence band as well as in the conduction band. If we keep on reduce the size of the nanoparticles to the still lower and lower and lower sizes around less than 100 nanometers, as you can see with the help of this picture, there is a complete discrete energy levels are formed, and now these discrete energy levels are separated from. So this shows that the energy band gap of the material will increase as we reduce the size of the materials to the nanoscale. This is the most important property, and which is all because of the quantum confinement effect. So now quantum dots. This is the one of the category in which comes under nanomaterials. Particularly quantum dots are made up of semiconducting materials, and normally it is believed that the quantum dot size is from 1 to nearly 10 nanometers. So the semiconducting nanoparticles which are having the size less than 10 nanometers, we consider them as quantum dots. So what are the important properties of the quantum dots and how it affects? See, here it is clearly mentioned that changing the band gap of the semiconductors is the most attractive due to fundamental and technological importance. Because widely tunable bandgap semiconductors are considered materials for new generation flat panel displays, photovoltaic, optoelectronic devices, lasers, sensors, and photonics bandgap devices. So we can easily tune the bandgap of the materials by we adjusting the size of the nanoparticles. The major properties of the quantum dots are listed here. One is they have a high extinction coefficient, they have a high spectrum of absorption, and they have a high electron mobility, bandwidth and position adjustment is possible in case of quantum dots. And we have a different adjustable, programmable optical properties, thermal properties with the help of quantum dots. Yeah, what now let us come to the most again where we are using these quantum dots, in which fields we are using nowadays. So as I can see, we are using these quantum dots in almost all fields of science and technology. So here clearly it is given that uh, we can use these quantum dots in terms of photoconductors, in the field of photoconductors, photodetectors. In the area of light emitting diodes, we can use photovoltaics, we can use in the area of biomedicine and environment, we can use. So even we may use them in catalysis and others. So in the second graph, I have shown that these quantum dots may be used in photocatalysis, biomonitoring, drug delivery system, gene delivery system, optical sensors, photoelectrochemical water splitting, electrochemical luminescence we use, chemiluminescence, light emitting diodes, photovoltaic solar cells. So I think from the last 5 days, we have seen these quantum dots and especially in different fields then. They are already in the previous sessions, we have discussed so many things which are related to quantum dots and their applications. So now my particular area of discussion here is bio-nano interfaces then. So in order to understand that, let us understand what is there existed in the universe first, in the nature. And from then we will, from that experience, we will learn how best we can create the bio-nano interfaces with the help of our experiences. See, some of the examples are given here. The lotus grows. I think in the previous discussion also it was discussed. The lotus grows in a small lakes and ponds. It is, as you can see, it is completely cleaned. The leaves, the layers of the lotus leaves are completely cleaned, and it is all because of the water droplets which are formed on that, and the layer of the leaves are mainly have the property of nano materials. The water drops acts like the water drops acts like a drop of hello. The water drops acts like a drop of mercury on the lotus leaf and slides slowly over the surface, thus sweeping away any dirt and dust accumulated on the surface. That is why it is always cleaned then. So nowadays, these kind of technologies are used in self-cleaning paints also. With the help of by learning this one, nowadays I think in the previous discussion it was discussed that hydrophobic paints were discovered which cleaned by themselves. This is a one more observation we can make. One is gecko. What is this gecko effect which is already existed in the nature? As a result of billions of years, we are able to examine in detail the most developed form and structure examples that are most suitable for living conditions. With modern electron microscopy techniques, one of these is ability of lizards known as the gecko effect to move rapidly in all conditions. So this is the live example of the nanotechnology which is present already in the nature. Well, so what are the modern applications of these nanomaterials? Where we are using them? The applications of nanomaterials in biomedical field, in construction materials, in electronics and energy storage devices we are using, and environmental remediation we are using, food packaging, processing and agricultural field we are using, and even in our renewable energy resources we are using. So the nanoparticles, which are of typically 1 to 100 nanometer sized, they are particularly used in carbon nanoparticles in the drug delivery systems, biosensors, in the biomedical field I'm talking, bioimaging, pollutant removal, fuel cells, catalytic reactions, sensors, and in medicines, nanomedicines, water treatment, sensors, antibiotic agents, they are, and gold nanoparticles are being used in photothermal, photodynamic, gene, and biolabeling, biosensors, and platinum. Platinum-based nanoparticles are being used in catalyst, automobile exhaust, gas treatment, fuel cell, and petroleum refining, and even organic synthesis process. The fields of applications of nanoparticles are extremely wide and continue to expand every day. A very good analogy is spheres with an increasing diameter because it exhibits non-linear changes in applications. Thus, the most notable areas of applications of new materials are medicines and biotechnology, obtaining materials with special properties, new materials for the production and storage energy. So particularly, let us come to the biomedical field, nanomedicines and drug delivery systems. How it works then? Due to their size effects and shape functionality, nanoparticle systems play a pivotal role in creation of DNA delivery vectors. They can penetrate deep into the tissues and are absorbed by the cell's efficiency. Nano-sized colloidal carriers of drugs can be regarded as an advanced development in pharmacotherapy. So gold nanoparticles and nanorods have many unique properties which have been explored for potential applications in biomolecular detections. So this is where I'm showing what are the different applications of gold particularly gold nanoparticles, because in the further slides I will go to the few examples, particular examples where we will understand how the bio nano interface is done and how to confirm the bio nano interfacing. In order to understand that, the brief theory or brief fundamental knowledge is required that I'm going to discuss in the first few slides. The gold nanoparticles of various sizes and shapes with the potential applications, here it is shown starts from A to P pictures. These all pictures depicts different types of typical types of gold nanoparticles. So here in the first picture A, the large nanoparticles, in the B, nanospheres were shown. In the C picture, nanorods are mentioned, and in the D, sharpened nanorods and nanoshells, nanocages or frames are shown. Hollow nanospheres are mentioned here, tetrahedron, octahedron, cubes, and rhombic octahedron, concave nanocubes. Various materials are mentioned in this slide there. So now come to the some basics related to the nanomaterials then. So what actually the nanoparticle here is, we used to say that nanoparticle, gold nanoparticle and something like that. It is not completely a bare, particularly a gold nanoparticle. For example, I'm talking. So it is surrounded by some layers. We call them as the surface ligands. In order to maintain the stability of the nanoparticles, we have to have a certain surface ligands which are covered on the surfaces of the almost all kind of nanoparticles. Otherwise, what will happen? There will be agglomeration of the nanoparticles will takes place whenever we are synthesizing them, and they will combine together once again, and we will fail to produce the or synthesize the nanoparticles. In order to prevent this kind of agglomerations and coagulations, we have to introduce some kind of surface ligands on the nanoparticles at the time of synthesis process itself, so that successfully they will stay as a nanoparticle separately. Otherwise, the coagulation or agglomeration will take place. Then here, there are again various types of nanoparticles, core shell nanoparticles. What exactly this core shell nanoparticles? At the inside of the, for example, if you consider CD, SE bar ZNS, INP bar ZNS nanoparticles, quantum dots. Here, INP, indium phosphide, will act as the core material. On that, over that, we have a zinc sulfide layer. So over the zinc sulfide layer, again, we have some kind of ligands like polyethylene glycol, or some other ligands will be coated over the this kind of core shell nanoparticles. Core shell nanoparticle means inside we have one nanoparticle. Over the that core material, one more nanoparticle layer is covered, and beyond that, on that surface, once again we have the some surface ligands. So this is the main focused area in my presentation. The thing is, how exactly we are going to establish the nano interfacing? What are the different affinity probes, or what are the different techniques which are available in order to achieve successful interactions between the nanoparticle and our biomolecule? See, the main question here is, if we have a different biomolecule and nanoparticles, we need to combine them. We need to mix them so that nanoparticle and this biomolecule will undergo interaction. There will be some kind of covalent bonding or whatever different types of interactions will take place. There is a successful interaction. How to achieve this kind of interactions? It is not so easy as just by mixing nanoparticles and biomolecules. It is not so easy. There must be some kind of techniques. There must be some kind of affinity probes, there must be some kind of affinity probes are required in order to achieve the successful interactions. So out of them, I am going to discuss a few examples and few techniques in this presentation. Here, I'll go to the first one. What is the biomodification techniques? In that, thiol compounds are used. This is the first technique which is widely used in order to achieve the bio-nano interfacing successfully. Well, in this thiol compounds, what exactly the persons are doing, the researchers are doing? Nano material is taken. For example, particularly for thiol compounds, the metal nanoparticles made up of a metal material are taken. Just for schematic example, I am showing here, schematic diagram I have shown. This is one nanoparticle, and thiol compounds are taken. If these two are mixed together, what happens? The metal nanoparticles surface will be covered by the, thiol compounds. These thiol compounds have some binding sites. And now the thiol compounds plus nanoparticles will have the affinity towards the antibody or aptamers. These are the biomolecules where they will combine, and completely all these three compounds will successfully form one bio-nano interfacing probe. It is. Now it is ready to use. What is that? Inside we have a nanoparticle, metal nanoparticle, and over that there is a thiol compound. And now over the thiol compounds, there is an antibody or aptamer, particular aptamer. These three combining, they are forming the nano biomolecule interface sensors then. So here it is clearly one example is given. The simple example is hydroxyl groups. We may use hydroxyl groups over the nanoparticles, gold nanoparticles, or various carboxylic acids may be used in over the metal nanoparticles, and these have the active sites COO minus. These active sites will successfully interact with the antibodies or aptamers, because in case of various biomolecules, there are some amino acids. The amino acids NH2 bond, NH2 and this COH, they will both interact and they will form a amide bond formation. This is how successfully we can achieve the nano interfacing. So this is again, it is elaborately given in the second one more slide. How we are doing the modification with the thiol compounds. As I said in the previous slide, gold nanoparticles are taken. Over that, what are the different ways of thiol compounds we have? It may be a hydroxyl group, it may be a COH group, even it may be some amide bond. Even we have a different techniques. These all pictures are showing from 1 to 11. 1 to 11, these are different ways of attaching thiol compounds and different thiol compounds on the metal nanoparticles. So this particular first one, hydroxyl group, may interact with one particular antibody. Second one may interact with one more particular aptamer or antibody. So like that, from 1 to 11, the 11 may have a specific antibody or aptamer. It will successfully interact with particularly that antibody, and with the help of that, we can create the bio-nano interfacing then. So here, the different examples are given. The first one is what exactly it is, mercapto-1 under canolitase. So like that, you can, as you can see, you can read from this one. We have a different, the 11th one is a mercaptopropanoic acid. Actually, it is a MPA, which is widely used in order to get the successful nanoparticles. So the surface modification actually it is. Here the surface modification with the help of that, we may achieve two things. One is the stabilization of the nanoparticle during the synthesis process, as well as which helps in creating the affinity between biomolecules and nanoparticles. So this is the second technique, which is again being used in order to achieve the interactions between the biomolecules and nanoparticles. What is this one? Modification through the iodine-biotin interactions. So what exactly this iodine-biotin interactions then? So basically, this is very useful technique. No chemical reagent is necessary for strepta-iodine coupling. The nanoparticles are simply incubated with the strepta-iodine protein in a buffer solution that is followed by elimination of the unbound proteins from reaction media by centrifuge or filtration. In case of NHS and EDC, that I'm going to discuss in the next slide itself, carbamide procedure, strepta-iodine molecules are covalently attached to the nanoparticles surface through the amide bond formations between EDC activated carboxylic groups and primary amine groups, NH2 groups then. Eventually, what happens here, the nanoparticle surface covered with the strepta-iodine molecules becomes available for the modification with the desired biotin labeled affinity probes and establishing a sandwich type of sensing platform. See here. So now let us understand this one with a more clarity elaborations. Imagine I have a nanoparticles of all types. It may be made up of nanoparticles, metals, or any semiconducting materials. You may take any type of nano material here, and that nanomaterial is surface coated by strepta-iodine. Now, I have a affinity probe, antibody or aptamer. This is the biomolecule. And to that antibody or aptamer, I have to have a surface which is coated by biotin. Now, we know that strepta-iodine and biotin both will interact with the help of amide bond formations. Nanoparticle is now ready to get bond with the biotin. So this biotin is particularly attached to those particular antigen or antibody which we want to study. So now we can see this one. There is an interactions between strepta-iodine and biotin, which successfully forms one kind of bio-nano interfacing and coupling between the molecules. This system is now ready to target the biomolecules. In order to study the cancer cells, in order to study some particular biomolecules, now this system will act as a biosensor. Initially, this is a biosensor now, and after preparing all this, we can use this as any particular biosensors which we may target to cancer cells or any particular examples or cells. What are the different ways of interactions which takes place? The non-covalent interactions between iodine and biotin will take place, and the construction of nano biosensors based on strepta-iodine biotin interactions usually begins with the modification of the nanoparticle surface with the strepta-iodine molecules, which is again followed by incubation with the affinity probes that carries at least one biotin residue to bind with the strepta-iodine coated nanoparticles then. So the third technique I'm going to discuss here is, now we are going to design one more biosensor with the help of pi stacking interactions. In case of pi stacking interactions, what actually we are doing? Let us imagine I have a carbon-based nanomaterials. This carbon-based nanomaterials will bring closer to the affinity probe, which is made up of either antibody or aptamer. But the thing is, the antibody or aptamer, it must have the surface layer which is a fluorescent material, which must be having a fluorescence property. Now, there is an interaction between these two. If there is a successful interaction between the carbon-based nanomaterials and affinity antibody or aptamer, which is tagged with the fluorescent materials, we can observe the changes in the fluorescence properties of this what exactly the fluorescent moiety. Before coupling between the nanoparticles, this fluorescent moiety has a different fluorescence property. It has its own unique fluorescence property. Once upon coupling between the nanoparticles, it shows a different fluorescence property. This also confirms by studying into the fluorescence properties of this fluorescent moiety, we may confirm there is a successful coupling between the nanomaterials and our biomolecule. Now, so the whole system will act as a biosensor, and this system is now targeted to a particular interested biomolecule. So here what I have shown, with the help of the schematic diagram, we can understand. Here I may take the different examples here. Carbon based, generally you may take any carbon based nanomaterials. In order to use it as a biosensor, use it as a bio nano interfacing material, I have to have a different type of affinity antibody aptamers which are attached with the fluorescent moiety. First, I have to create this one. Where first I have to design this one. First, I have to synthesize. Then I have to target the molecules. See, presence of p electrons, how it takes place, it is explained here. The presence of p electrons both in nanoparticles and biological molecules has simplified the exploitation of this interaction to develop smart nanobio hybrids. The nanobiosensors built with p systems were mainly based on the carbon nanomaterials such as graphene and carbon nanotubes derivatives then. For example, nucleobases with aromatic rings can bind to the graphene surface with electrostatic interactions, hydrophobic forces, and pi-pi stacking interactions. One example I have taken here for particular the previous example problem, I have taken one example. Here, single-walled nanotubes, single-walled carbon nanotubes were taken, and these carbon-based nanoparticles were interacted with 30 FM carboxyfluorescein. This is a fluorescent moiety dye which is labeled to any aptamer or any antibody. It means what? Aptamer antibody is there. To that, I have a one fluorescent dye moiety which is attached. Now, single-walled carbon nanotubes plus this one second system will form an interaction with the help of pi-pi stacking, pi bond formations and all, were effectively utilized as fluorescent sensing probes for ochratoxin A detection. See, ochratoxin A detection is a biomolecule. In order to detect that biomolecule, I am using one biosensor. That biosensor is what? Which is based on a carbon-based nanoparticle. Initially, it is combined with the one aptamer and fluorescent molecule. So these three molecules will combiningly will be acting as a probe in order to detect the one of the biomolecule like a acrotoxin A detection. The essential point here is acrotoxin A specific DNA aptamers should be taken. It means our fluorescent molecule must be attached to the specific DNA aptamer, then only we can detect the particular biomolecule like acrotoxin. In the absence of the target, DNA aptamers and aromatic FAM labels interacted with negatively charged single-wall carbon nanotubes surface through pi stacking, leaving the fluorescent dye quenched as a result of the fluorescence resonance energy transfer, which I'm going to discuss in the upcoming slides what exactly the FRET means. So here in the red lines, I have given how this bio-nano interfacing will act as a biosensor. Second example also we may see here. This is very easy to understand. Graphene oxide nanomaterials are taken. So first of all, graphene oxide nanoparticles were taken. To that, what we will do, we will attach aptamer, which is the biomolecule, one of the antigen or antibody you may take, antigen or aptamer, which is initially it is combined with the one of the fluorescent moiety. That is a FITC is the fluorescence material it is. These two, FITC plus aptamers were one unit. Now this unit is combined with the graphene oxide. These two units will now successfully will act as one of the biosensor for particularly what? Particularly for HCG detector. HC is the one of the biomolecule which is used to detect confirm the pregnancy. Right. The example is explained here. What we'll do again, we will take the carbon based like a graphene oxide, and I have a affinity antibody or aptamer. To that, I have a FITC biomolecule. Fluorescent molecule. These two will interact first. there is a successful coupling between these two takes place, and the whole unit will act as the sensor now. These are the specific sensors, not the general sensor. This is not used for being used for any type of biomolecule sensing. Particularly, this kind of sensors are used for ACG here. It is designed for that purpose only. In the, what it shows here, a terminal fluorescein isothiocyanate, that is FITC, which is labeled to the aptamer, which will act as the sensor for human chorionic gonadotropin detectors, which is the biomarker for pregnancy. This is how we may use nanoparticles with the help of any affinity probes as a biosensors. Let us come to the one more technique. With the help of this one, we may achieve successfully how exactly we may create the biosensors then. See, EDC NHS chemistry. Here, EDC is usually employed together with N-hydroxysuccinamide NHS, that is NHS, to accelerate the reactions rate and the final coupling efficiency. Here it is clearly explained that we will take one of the molecule, EDC molecule, and now it will undergo interactions with the NHS. So in order to make it very clear, what I will do, so now there is an interaction between EDC and NHS. Two of they are very useful materials. And because of successful interactions between these two, we will get a stable material. And that stable material on the surface, it has some active sites, active binding sites. Like it may form a amide bond formation, or even it may form some covalent bond formation. Whenever this system is introduced with any target molecule, biomolecule, it will get a covalent bond formation or van der Waals force of attractions, or different types of interactions will take place. With the help of that also, we may successfully create one of the biosensors. See, carbamide molecules how they are useful compared to other techniques then. Carbamide molecules are considered as zero-length cross-linkers. Unlike the previous modifications, what we discussed so far, surface modifications, streptavidin, biotin and streptavidin, and other with the pi stacking also. Those were the three systems we discussed. And this is the fourth, how it is useful as compared to the previous three techniques then. So method EDC NHS carbamide reactions produces a strong covalent bond between the reaction compounds and reinforcing the lifetime of the conjugation. This is the advantage. With the help of this EDC NHS chemistry, we achieve a stable, a successful, and constant conjugation between the molecules. So it is little bit less in previous techniques. And because of all proteins, like antibodies, are composed of amino acids that contain a primary amine and carboxylic acid groups, we have NHS EDC reaction can be used to bind biomolecules to any surface comprising primary amine or carboxylic acid groups. See, what the meaning of this sentence is here. With the help of this chemistry, EDC and NHS chemistry, the same combination is used for many of the biomolecules. You may target many of the biomolecules with the help of the same biosensors. But in the previous examples, as I said, they are specific biomolecules targets. With the help of the single biosensors, I may not study the various different biomolecules. But that is done with the help of this EDC NHS chemistry. I may use this sensor in order to study various number of several biomolecules. That is one of the advantage of having this technique for the surface modifications. With the help, what is the example for this one then? So for EDC and NHS chemistry, I have particularly taken one example, one biosensor, which is used in order to detect the Alzheimer's disease. I think most of you people heard about Alzheimer's disease, right? So this Alzheimer's disease can be detected with the help of biosensors, a simple technique. What we are going to do in this technique is, let us take a single nanoparticle, single wall nanoparticles, which is now coated with, as I said, mercaptopropanoic acid, MPA. Now nanoparticle, the surface layer is mercaptopropanoic acid. This is one part of that. Second part is EDC and NHS. This is the second part. EDC and NHS is it has the ability to form a covalent bond with almost all types of antibodies, right? Particularly this EDC-NHS in this case, it is attached with one of the antibody, particularly what antibody it is? Alpha-1 antitrypsin antibody. This antitrypsin antibody is always particularly binding the antigen present in the Alzheimer's disease. Remember. So whatever the antigen present in the Alzheimer's disease, if the person has the Alzheimer's disease, he has some particular antigens. That antigen successfully binds with the antitrypsin, right? For that reason, what we will do, our nanoparticle and plus EDC-NHS plus antitrypsin antibody is taken. These three will act as a sensors. Actually, these are the biomarkers now. In the absence of the nanoparticle, in the absence of this EDC also, this antitrypsin binds to the Alzheimer's disease. No problem. There is no issue in that one. But how we will come to know that there is an interaction, there is a binding between antitrypsin and Alzheimer's disease. So in order to detect, visualize that one, in order to mark it, we are using some signals giving systems. So these nanoparticles will act as the signals, which will, whenever this antitrypsin gets binded with the Alzheimer's disease antigen, it gives some signal in terms of fluorescence, in terms of some changes in the properties. By looking into those properties, we will confirm there is a antigen which corresponds to the Alzheimer's disease. So silver nanoparticles were taken, which are now combined with the MPA, mercaptopropanoic acid solutions then, and then the thiol groups were introduced, which have a carboxyl groups on the surface. And this now carboxyl group, one thing, and another thing is EDC-NHS. It has a amide bond, NH2, amine group it is. So whenever we mix these two, NH2 and carboxyl groups will form amide bond formation. There is a successful interactions. There is a successful bond formation. We can confirm that one. Later on, because anyway, this EDS and NHS is already bonded with the antitrypsin, we will introduce this system in the person who has Alzheimer's disease. Just imagine whether he has Alzheimer's disease or not in order to check it. So suppose if he has Alzheimer's disease, he has some antigen, particularly that antigen will bind with the antitrypsin. If it binds with the antitrypsin, the properties of the silver nanoparticles will affect. When it was completely free, when there is no interaction, when it is completely isolated, the nanoparticles fluorescent properties were studied and they are calibrated. This is what the pure nanoparticle properties like that. Upon binding with the antigen, now there will be we will observe, we will notice there are some changes in the nanoparticles. So if there are changes, we will confirm, okay, now there is some kind of antigen which is corresponds to Alzheimer's disease. With the help of this kind of studies, we will confirm Alzheimer's disease then, which will act as a biosensors. This is one example for the previous surface modification techniques. Well, dear participants, so far whatever I have discussed, it is what are the different techniques. With the help of them, we will get a successful biosensor. Now I have a successful biosensors which is now ready to act, which is now ready to use for biomolecules targeting. The question is how to confirm them, whether there is a nano interfacing has taken place or not. In order to confirm, I have to use some of the techniques, because just by mixing, I cannot say that there is a bio-nano interfacing has taken place. I have to prove it, right? In order to prove that one, we have a different experimental techniques. The one here I have listed 4 of them. One is you may study the absorption properties of that system. Whatever you have produced, you have designed the bio-nano sensors. With the help of this absorption technique also, we may confirm there is a successful interaction or not. And even we may go to the gel electrophoresis, and there is a circular diagram, CD spectrometry we may use, and DLS, dynamic light scattering technique we may use. Here I have listed only 4 of them. Still there are many techniques. With the help of those techniques, we may confirm there is a successful biomodification is done or not. Well, let us see one by one how they are useful, how we will confirm with the help of the absorption spectroscopic technique. See, UV absorption spectroscopic is a standard tool for the characterization of nanobiosensors. What we will do here is, Affinity proofs, oligonucleotides based aptamers and protein based antibodies also show some typical absorption peaks around 260 around and 280 nanometer with the UV visible techniques. So this 260 and 280 nanometer absorption peak of almost all antibodies and aptamers is when it is at isolated state. Whenever it binds with the nanoparticle, whenever it binds with the biosensors, this 260 nanometer or 280 nanometer absorption peak position will change. By looking into the peak position, change in the peak position, we may confirm that, okay, now there is a successful binding has taken place. When it isolated material, isolate the properties 260 and 280 peak position. So upon a successful interaction coupling in the nanoparticle and the biomolecule, this property will change. That is absorption property. By studying this also we may study. Particularly full width half maximum property, noticing this one, we may confirm that the interaction has already taken place. This is one technique. With the help of this, we may confirm. The another technique, see here it is with the help of graphs, and I have shown how it varies. You may notice this first graph in the A picture. In the first graph, I have taken bare particles. Bare particles. Second one is a conjugated particles and aggregated particles. So the blue line is when it was a bare particle. There is no interaction. It was completely a free particle now, free molecule. And when it undergoes the interaction with the nanoparticle, there is a change in the peak position, absorption peak position, nearly around 3 nanometer. But one particular example it is that shows a successful interactions. And like that, here there are various examples are mentioned, particularly for gold nanoparticles. I may see that for red, there is a blue shift in the nanoparticle positions. So 260 nanometer was the absorption peak position when it was a bare, and upon introducing some interactions and upon designing the nanoparticles, there is a change in the peak positions. So altogether, what is the summary in the first technique? How we will confirm? So by knowing the peak position, absorption peak position of the biomolecule before tagging, before coupling, and after coupling, by looking into that, we may differentiate there is a successful interaction has taken place or not. This is one confirmation. Okay. So now, dear participants, this is the second technique. This is again one of the widely used technique in order to confirm the interactions. Gel electrophoresis. So the gel electrophoresis, what happens? The one common knowledge everybody has is whenever the size of the particle is large, it moves little bit slower. If I have a small particle, counterpart of that one, I have a small particle. When it is the two particles which are started from the same point, they are running. Imagine heavier body will move a less distance and a lighter body will move a larger distance, right? So when if I have a nanoparticle and a biomolecule, if they are two separate moieties, particles, if they are now, if I say them to move a certain distance, now they are moving a very with a high velocity, with a large velocity, they are moving then. They will cover a larger distance, correct? In any liquid, if I introduce them, they will move a larger distance because they are completely separate molecules. They have a ability to move a larger distance then. Imagine if I combine them, A material plus B material, if I combine them, now it is a single moiety. If I tell it to move in the same liquid in the same time, whether it covers the same distance? No. So best example is what happens. It covers a less distance. It stays in the say almost all in the same positions. So by taking the picture of this one, I may confirm whether there is a combination of A and B has taken place or not. When so see, you can see here the picture shows the first one. When there is a pure material, it has covered almost all distance, single quantum dot it is. There is no modification. There is no quantum biosensors are designed. Only purely it is a quantum material and it covers a large distance. If I introduce something else like a biomolecule and it covers 0.3 concentration with a different concentration I'm talking here. If I introduce a 0.3 of biomolecule, it covers a less distance. You may observe some pictures here, diminished pictures. Imagine If I directly, I will go to the 39. It is another higher concentration. So high concentration of biomolecule is introduced. And now this is a nanoparticle or quantum dot. Both are successfully combined and hence they cover a very less distance. It has to cover from here to here, right? In which when it was a pure isolated material, it has covered this distance. Now it covers very little distance. With looking into this one, I can confirm successfully that there is a successful interaction has taken place. That is why it is not moving a far distance. So this kind of technique is known as gel electrophoresis technique, which is conducted with a specific environments and specific criterias, right? So another technique, the third technique which is being used in order to confirm is circular dichroism technique then. What exactly the circular dichroism technique, which is based on polarizations, absorption of polarized lights. So any chiral materials, I think most of the chemistry persons will understand chiral materials or chiral molecules. They have the ability to absorb the polarized lights then, right? So usually the biomolecules are having the ability to absorb the polarized lights. Most of the nanoprobes utilized in biosensing applications do not show dichroic behavior in the UV spectrum. Normally, the nanoparticles will not show such kind of property, but so here it helps in a CD spectroscopy can easily surpass overlapping absorption responses and deliver precise structural informations. Therefore, a CD technique can be performed to evaluate a conformational changes of antibodies and aptamers upon binding to the nanomaterial. See, the chiral molecule, biomolecules, almost some of the biomolecules are the chiral molecules and they have the ability to absorb the polarized light then, not the not the nanoparticle. Upon interaction with the nanoparticle, there will be a conformation, structural changes. We will observe in the biomolecules then. This structural change in the biomolecule will affect the chirality of the biomolecule then. If it affects the biomolecule chirality, then it subsequently affects the absorption. CD spectroscopy will be disturbed. Disturbed in the sense we will notice different CD spectrum. So the pure biomolecule has a different CD spectrum. When it interacts with the nanoparticle, it has a different CD spectrum there. By comparing these two, when it was isolated, when it is a pure. So if we compare these two with by knowing and by practicing, by recording the values and data analysis with the help of analysis, we will definitely confirm there is a successful interaction. Because if there wasn't a successful interaction, I should have a pure the CD spectrum which is equal to the pure biomolecule. But I am not getting the previous CD spectrum which I have taken for the pure biomolecule. It is not similar now. It is different. It means there is a disturbance. There is a structural change in the biomolecule. Okay, this is the third technique we are using. That I have explained with the help of some of the graphs here. This is the CD spectrum. The black line, what it shows, as I said, they don't have any chirality. The quantum dots will not absorb any polarized lights. So that is why it shows a straight line. And now the red line is one kind of a biomolecule and which is now combined, see, which is already combined with the
Hello. Sir, your share the screen, sir. Share the screen.
Sir, I'm audible. Is it audible, sir?
Yes, sir. You are now audible, but your screen
yes,
is not visible, sir.
There is a network issue here, sir. Just a minute, I'll share, sir. Yes, sir. Please confirm, sir. Is it visible now?
Yes, sir. It is visible now.
Thank you so much, sir.
Okay.
So now, what I was talking about the biomolecules, antibodies, and nanoparticle interactions. Then this is another example: nucleic acid-based aptamers we may use. One example it is. Let us compare which one is better option then. See, if I use the antibodies or aptamers for targeted biomolecular interaction studies, both this antibody is a protein and aptamer is a DNA or RNA based peptide it is. So if I compare the sizes of these two, antibodies are nearly 100 to 180 kilodalton. They have the size of around 10 to 15 nanometer. But aptamers are little small size particles, 2 nanometer size, and their molecular weight is 5 to 30 kilodalton. And where I can use the antibodies for the targeted materials, it is limited to some immune responses. But aptamers may be used for various applications like ions, nucleic acids, proteins, whole cells, toxins, and chemicals we may. And what about the cost? The antibodies in vivo production is done, and because of that, they have a high cost. And aptamers production is done in vitro also, and hence they have a cheaper as compared to the antibodies. And physical stability. As I said while explaining, sensitivity to temperature requires a strict refrigeration. Means I have to maintain some specific conditions for successful working of the antibodies. And aptamers, high temperature resistance. They have a high temperature resistance and they can be lyophilized for extended shelf life. Then, and what about the chemical stability of the antibodies? So they have a low chemical resistance, low pH resistance. And what about the aptamers? Aptamers have a counterpart. They are really good as compared to the antibodies, right? So now, apart from these two, aptamers and antibodies. Hello, sir.
Sorry to interrupt you.
Yes, sir.
Some of the participants are not able to hear.
Yes,
Sir, are you using the Bluetooth or?
No, sir. The direct microphone I'm using, sir. It is audible to you, sir.
It is audible to me, sir. For me, it is audible. And how many participants?
Please tell me.
Some of the participants are unable to listen.
Please, dear participants, those please confirm whether it is audible or not.
Please confirm, dear participants.
Audible, sir, audible.
Yeah,
Audible,
thank you.
Audible, sir.
We
Thank you.
can go ahead.
Sir.
Yes, sir. Sir, go ahead, sir.
Yes, sir.
Okay.
Is the PPT available now? Is it available? Okay. Yes, thank you.
Sir, make
so now,
it large, sir. Make it large.
Yes, sir. Now we'll go to the semiconductor nanocrystals, quantum dots. So there are vast applications of the quantum dots. Their size is less than 1 to 10 nanometer. It is between 1 to 10 nanometer. They are being used in optical applications, quantum computers. Particularly, our main focus area is the biological applications. They are being used in bioimaging, biosensors, diagnostics, drug delivery systems, and therapeutics. Then, Okay, but the question comes, what kind of nanoparticles I have to use then? Especially when it comes to the biological field, I must be very specific because it should not be very carcinogenic. It should not be very damaging. It should not damage the cells of the human bodies or any animals, right? So this, in order to avoid these problems, so many scientists and so many researchers have already reported that the nanoparticles or quantum dots which are based on CDS, cadmium, which are based on uh, cadmium, mercury, selenium, and these are lead. These are almost a little, they cause some carcinogenic to the human systems or cells of any biological system. For that reason, the another group of the research, what they have done, they have used other materials in order to synthesize the quantum dots, which are less carcinogenic, which damage less to the biological system. Then one example of that one I have taken here, which based on that quantum dot, I have done the work. That is the indium phosphide zinc sulfide. Then here, I have compared the effect of carcinogenic effect of the CDSA bar ZNS and INP bar ZNS quantum dot. As you can see from this graph here, the release of the cadmium ion is more as compared to the indium phosphide zinc sulfide quantum dots. So therefore, let us prefer less carcinogenic materials like indium phosphide bar ZNS quantum dots. Here I have taken such a quantum dot. This is the report where it is shown the INP bar ZNS is the one of the best safer alternative to our wherever we are using the CDSA bar ZNS quantum dots or any carcinogenic or any heavy metal based quantum dots may be replaced with our greener indium phosphide zinc sulfide nanoparticles. Well, advantages I have listed here. What are the different advantages of the indium phosphide then? Both are semiconductor types. One is a this one is a second of sixth group of that one. And what is the energy band gap of the this first one type? It is 1.8 electron volt, and for this one it is nearly same 1.5 electron volt. And emission range, it is in the visible region. Both have the visible region. Even INP bar ZNS quantum dots even in the covers in the IR region also. So their structures are different. It is one is a Woodside zinc blend structure and another one is a zinc blend structure. And quantum yield means how much they give the fluorescence. They both have the higher efficiency. And what is the biocompatibility, whether they are suitable for the studies or not. So they are one is in vitro suitable. The first CDC bar ZNS quantum dot is suitable for in vitro studies, and your our INP bar ZNS quantum dot is suitable for both in vivo and in vitro studies. Their toxicities, cadmium-based nanoparticles will release the cadmium ion, which is dangerous to the health, which is dangerous to the biological system, but there is no photo degradation is observed in our system then. So now I will go to the one particular example. Sir, I think I have a time, right? Shall I go to the next part?
Yes, sir. Yes, sir. 5 minutes.
Yes. Thank you, sir. So there is an interaction between biocompatible pegylated, polyethylene glycol, indium phosphide, zinc sulfide, quantum dots, which are now interacted with the bovine serum albumin protein then. What are the chemicals which are being used here? I have taken bovine serum albumin protein and then this quantum dot and buffer solution is required. In the second case, I have taken HSA, that is human serum albumin, and PEG, coated quantum dots, and PBS buffer is required. In the third case also, we have taken third examples in this presentation I am going to discuss. I have taken crystal violet, some dyes I have taken and some solvents are used. Right. Let us go to the first one. How the samples were prepared first one. I will take a quantum dot that is surface coated, surface of the quantum dot is coated by one polymer, polyethylene glycol. For the stability purpose, for biocompatibility purpose, I have used that one. And in another case, we will take a proteins or dyes, whatever I want to study. Both will be mixed together in a buffer solutions, and that their temperature is maintained at around normal buffer conditions, 7.4 or 7, around 7. And then the sample is used for the further studies with the help of different experimental techniques, absorption studies, fluorescence studies, and lifetime studies. And these are the three studies. And another thing is synchronous fluorescence measurements were also done then. Okay, what is the importance of this protein I have studied then? So let us look into this one. The size is almost the molecular weight of this one is 66.5 kilodalton, and it is the most extensively studied abundant protein. And the total how many number of amino acids are there here? 583 amino acids are present. 17 disulfide bonds are there. 3 homologous domains and 9 loops were present. This is what the structural analysis of the bovine, serum, albumin, whatever. And here there are two moieties. One is tryptophan, another one is a tyrosine there. These two moieties amino acids are fluorescent. So if I take the fluorescence studies of this bovine BSA molecule, I will get some fluorescence because of tryptophan and tyrosine molecule. So, and what are the advantages of this one? It acts as the carrier for endogenous and exogenous transports drug delivery systems. These are the advantages. Okay. So now, after preparing the samples, I have studied the synchronous fluorescence study of these samples then. With the help of this SFS study, what I will come to know? I will come to know which molecule is, because in the BSA molecule, there are two fluorescent moieties, tryptophan and tyrosine. Among these two, which one is contributing more? Which one is interacting more than? Which one is undergoing interactions with the nanoparticle? I have to be sure that whether it is a tyrosine or whether it is a tryptophan molecule. That can be assured with the help of synchronous fluorescence studies then. Here, in this study, the results shows that there is a blue shift in if there is a blue shift in the fluorescence intensity, now we will confirm it is undergoing hydrophobic interactions. Suppose if there is any red shift in the fluorescence intensity and position, we call it as a hydrophilic interactions. If there is no shift, only there is a decrease in the intensity of the fluorescent molecule. Now we call it as there is a conformational changes. There is a change in the size or shape of the biomolecule then. These are the spectra we got for the BSA and HSA molecule. Here you can see there is a change in the intensity of the biomolecule. And here this is what the increased intensity of the another molecule then. Okay, now we'll come to the UV visual absorption spectrum of the system we have taken. BSA system plus nanoparticle. This is the combination I have here. So that we call it as a conjugates, biomolecule conjugates. Nanoparticle plus BSA conjugates then. I have taken the absorption spectra of such molecules. I noticed that whenever I increase the concentration of the quantum dots, for example, BSA is the constant. It has certain absorption peak here, position at around this position, the 280 nanometer. And whenever I keep on adding the increasing the concentration of the nanoparticle, I observed that there is an increase in the absorption spectrum. Intensity, absorbance is increased then. This increase in the absorbance, is there any shift in the absorption positions? That also we will see. If there is a shift, we will analyze it in a different case. Here, I noticed that there is no shift in the position of the fluorescence spectrum. Only there is an increase in the absorbance. What it shows? It shows that there is a static kind of quenching is taking place. Static means biomolecule will combine with the nanoparticle with the process of static interaction. There it is not a dynamic interactions then. So this is a one kind of a static quenching we observe. Well, later on, after a synchronous fluorescence study, after absorption studies, we will going for the next part of that fluorescence quenching of the BSA molecules. Here, the procedure is very simple. We will take the BSA plus quantum dots. We will mix them. We will combine in order to study whether there is a successful interaction or not. What I will do with the different various concentrations of quantum dots upon adding to the BSA, I will study the fluorescence properties. So when it was a very pure material, only the BSA protein material, it has a high intensity. Upon adding the quantum dot to it, little bit, there is a decrease. What I observed, there is a decrease in the fluorescence intensity. And further, if I still add more quantum dots, concentration, if I increase, still there is a decrease in the fluorescence intensity. So this is how, if I keep on increase the adding of quantum dots, I observe there is a decrease in the fluorescence intensity of BSA molecule. Particularly, it is for tryptophan there. In the inside figure shows that even there is a shift in the peak position. So by increasing the quantum dot concentrations, adding to the BSA molecules, there is a shift in the peak position. That is a blue shift. What it indicates, now BSA molecule plus our quantum dots, greener quantum dots, heavy metal free quantum dots, undergoing hydrophobic interactions. Our tryptophan molecule is undergoing to the hydrophobic region, right? This is one we noticed, which confirms the successful affinity between the two moieties. The second graph is a Stern-Molmer plot, which also confirms what kind of interaction. Is it a static or is it a dynamic? So see what I will clarify what the first thing, what is static process and what is dynamic process. Static is nothing but when the two molecules will form together, A plus B, it will give some component, another component then. But during the dynamic pinching process, what happens? The A molecule is stagnant, B molecule will pierces, it interacts, it passes through the A molecule. That is a kind of a moment we observe, and that is a dynamic pinching will takes place here. Okay, the Stern-Molbar plots confirms whether it is a static pinching or dynamic pinching by looking into the values of that. And this is the equation. With the help of this equation, we will calculate the KSV values. That is the Stern-Molbar constant or bimolecular pinching constant also. Well, the fourth study is TC-SPC study. The TC-SPC study is the one where we will study the fluorescence decay lifetimes of the fluorescent molecule. So as I said previously, whenever any molecule, if it is exposed to certain suitable energy, it undergoes excitation, and during the de-excitation process, how much time it has taken. So normally what happens, the average lifetime is for this VSA molecule, it is 6.09 nanoseconds. It is purely. Whenever we add some external quantum dots to it, its lifetime has changed. The lifetime is now reduced to 5.8 nanoseconds and even lesser. Again, it depends on concentration. So if you increase the concentration, still there will be a decrease in the fluorescence lifetime of the BSA, which also confirms the successful interaction between these two then. Well, this table here, the data, what it shows here, you can see for 0, it is a pure BSA molecule. It was a 6.09 nanosecond fluorescent lifetime. And for 1 concentration, the lifetime has reduced to 5.8 nanoseconds then. So we will go to the temperature dependent fluorescence studies of this system, BSA plus quantum dot system then. What I have done here is, I have studied the fluorescence properties, no doubt, but at different temperatures. At normal temperature, the temperatures are given here. At 288 Kelvin, I have studied the fluorescence properties of the same system, of the same combination, and at 298 it is done, and at 308 Kelvin it is done, and at 318 Kelvin, normally at room temperature, the fluorescence properties are studied. By studying with respect to the temperature, we will come to know what kind of interactions are taking place. So to make it very simple, with the help of temperature dependent studies of biomolecules and nanoparticle interactions, what results we will get? The results are, what are the type of interactions? Is it hydrophobic or hydrophilic? This kind of result we will get. Another thing is, we will come to know what kind of what is the energy, whether it is a energy is released during the reaction, or is it an exothermic reaction, or is it an endothermic reaction. That also we may confer with the help of the temperature dependent studies. Then we may calculate the Gibbs free energy also. So I think I have given in the next slide the list of all the parameters here. So based on temperature dependent studies at different temperatures, this one is a Stern-Molbar constant I got, and bimolecular pinching constant is also listed here, and this is the binding constant is listed, and this one is the Hill's coefficient. N is the Hill's coefficient. Based on this, what it suggests, this N suggests that how many number of particles are interacting with the one biomolecule. That also we may decide with the help of Hill's coefficient. So that this equation helps us to calculate these parameters, Hill's coefficient and other parameters then. See, as I said, the type of interactive forces in bioconjugation may be calculated based on these equations, Gibbs free energy equations, enthalpy equations, with the help of binding constant. And I have calculated them and I have listed in the table. So we will confirm, I mean, we will come to know entropy I have calculated, then enthalpy I have calculated then. So what are the confirmations then? There is a successful, we may ensure that binding process is a hydrophobic and it is an endothermic process because it is absorbing the energy, right? So now we will study the energy transfer between the BSA molecule and quantum dot. These are the parameters. These are the parameters I got from FRET studies. In the previous slides, I explained what exactly the FRET study. Here, our BSA molecule will act as a donor, and quantum molecule will act. Quantum particles will act as the acceptor molecule. So whenever we excite the BSA protein molecule, biomolecule, it undergoes excitation at 280 nanometer and it gives the energy around nearly at 350 or whatever. So there is one property for nanoparticle. They have a higher extinction coefficient, means their absorption spectrum is very large, right? So even they absorb up to at 300 nanometer, 400 nanometer also. So our INP bar ZNS quantum dot will absorb successfully the energy emitted by the BSA protein. So with the help of non-radiative process, with the help of FRET process, the INP bar ZNS quantum dots are absorbed and now they will give certain fluorescence then. These are the parameters which I have studied, and based on these parameters, I can assure you that the efficiency what we observed is very less. It is important actually it is. The FRET efficiency is very less. What is the meaning of that one? The less efficiency indicates that the biomolecule and quantum dots are undergoing static interactions, not through dynamic quenching processes, which is one of the basic step in designing our bionanosenses interfaces then. Okay, this poster distance R0 is a poster distance for various systems. I have compared my result with various other results also. BSA molecule is studied with various other quantum dots, and these all established results are in correlation with our studies there. So what is the summary of, whatever we studied in this one, we studied the binding mechanism between model proteins BSA and non-toxic biocompatible nanoparticles. We observed the Bliss shift in tryptophan fluorescence, which indicates there is a hydrophobic microenvironment, and quantum dots are completely binding to the tryptophan residue, not to the tyrosine residue. Fluorescence quenching is due to ground state complex formation, that is static quenching phenomena. However, at high temperatures, normally what happens at a high temperature, there is a detaching process will take place. Both will detach. Biomolecular nanoparticles will separate from each other. Hence, static quenching process will dominate at high temperatures. And thermodynamic studies suggested bioconjugation of BSA and quantum dots. Further, the affinity of quantum dots for BSA is independent. Based on this one, it is independent. Okay, this is a similar explanation. I think this is for other protein. Same nanoparticles with human serum albumin. So here the properties are given. I think I will skip this one because there is a similarity between HSA protein and BSA proteins. The same kind of studies are taken. And now I will, at the end of this study, I will come to know what kind of interactions are taking place between HSA, human serum albumin, and our nanoparticles then, like BSA molecules, right? So better, I will go to one more part of this one. This is the interactions in order to clarify, in order to make it very clear. Now there is a kind of FRT is taking place between human serum albumin protein and INP bar ZNS quantum dots. Okay. I think this is all related to the HSA. See, it is a similar result. FTR results are taken. Well, now the CD spectrum it is that. CD spectrum for the HSA protein plus INP bar ZNS quantum dots are taken. I told you, CD spectrum is used in order to confirm structural changes in the interactions. If it was a pure material, if it is a pure material, the structure will be something different structure it has, and it gives us a different circular dichroism spectrum. Once it attaches with some external particles like quantum dots, the structure will change. The change in the structure will appear in the form of spectrum, circular dichroism spectrum. So that we can decide based on this one. This is a summary of the second one. Well, this is another parameter. We have taken a different molecule, biomolecule. The spectroscopic and molecular interaction study of trypsin from bovine pancreas and coumarin 440 dye. This is the organic dye we are taking, and bovine pancreas biomolecule we are taking then. Here we have done almost all similar, but absorption spectrum we have studied, fluorescence spectrum we have studied, temperature dependent parameters also we studied, what are the interactions then, and even we have studied the theoretical modelings like a computational analysis, like molecular dockings were also studied in this one then. So the role of, what is the role of the trypsin molecule then? The role of the trypsin molecule is it is a serine protease found in the digestive system. It plays essential roles in digestion, growth, and cell differentiation. And what is the structure, molecular structure? It comprises of 245 amino acids. Its volume is given, and which contains 6 pairs of disulfide bonds then, which is hyperactive of trypsin. Elevated trypsin activity is linked to various conditions then. Overall, this trypsin, which is extracted from the pancreas of the human pancreas organ, which has with this kind of structures and which is having some fluorescent, moiety like trypsin there. Now our goal is again same. What is the goal? Whether trypsin molecule present in the pancreas organ which is extracted, does it interact with the nanoparticle or not? So before that, does how it interacts with the organic biomolecule? One of the organic molecule we have taken, that is a coumarin 440. So absorption spectrum is taken. We notice that there is a successful interactions by noticing the decrease in the absorption spectrum. Okay, fluorescence spectrum indicates there is a decrease in the fluorescence intensity of the trypsin and increase in the intensity of the C440 organic dye. There is a successful FRT is taking place. Non-radiative energy transfer is taking place between the trypsin molecule and biomolecule and coumarin 440 molecule. In short, I am explaining this one here that because you know the conditions, different conditions for the FRT. The emission absorption spectrum of the acceptor must be equal to the emission spectrum of the donor. This is the Stern Volmer plots, which is used to calculate the energy efficiencies and all. Time resolved spectrum confirms there is a dynamic quenching is taking place, not the static. Previously, it was a static quenching. Here it is a dynamic quenching. Dynamic quenching is one. Whenever the protein molecule is excited, our coumarin 440 organic molecule is moving through that one excited molecule. It undergoes collision, and by then trypsin molecule comes to the ground state and energy is being absorbed by the C440 molecules then. These are the different spectrum based on the thermodynamic analysis we have taken, and I have explained Hill's equations and binding constants were determined, which helps us to decide what kind of process, endothermic, exothermic processes, and whether energy is released or not it is, and whether hydrophobic interaction is taking place or not. The positive delta S entropy indicates exothermic reactions, and the positive delta H here indicates intermolecular bond formation is taking place. Both delta S and delta H contribute to hydrophobic interactions, and our free energy Gibbs free energy delta G helps to determine spontaneity of bioconjugation. Right. So molecular docking will also one of the best technique in order to confirm the binding sites. Right. So based on the molecular bonding, docking results, I have tabulated these results. And the conclusion of this study is trypsin. There is a the spectroscopic analysis reveals the formation of trypsin and 440 complex, right? And there is a hydrophobic interaction, spontaneous exothermic processes were taking place between these two. So these are the papers we published and summary and inferences of the previous studies. Well, there are a lot of scopes in this field. And even I have one more part of this one. I think I will skip because there is a little bit of time restrictions. I think it is around 5:15 and 5:20. So now I will go to the conclusion part of this. Yes, we may use these other quantum dots in various other purposes. What are the future challenges? So the future challenges are listed here. So well, at the end, I would like to thank all the KLSVDIT Haliyal management and our beloved principal sir, Dr. V. Kulkarni sir. And also I thank Dr. Samir Galgali sir for his constant support and always encouraging. And I thanks to all my research team and co-workers and my colleagues. Thank you one and all. Hello, sir.
Yes, sir. Thank you so much, sir. Indeed, it was a very vast and very interactive session. No doubt, your work speaks a lot, sir.
Thank you, sir. Thank you so much.
Yes, participants, we have another 4 minutes to go. If you have any questions to ask, you are most welcome. Our next speaker, Dr. Arun, is also in the meeting. He will be also eagerly waiting to join you all. Dear participants, do you have any questions? Dear sir,
Yes, sir.
sir,
Shall I
I
stop?
guess, yes,
Yes,
sir, you can stop sharing now.
Yes, sir. Thank you, sir.
Okay. Uh, if you, sir, can you post your telephone number, email ID in the chat box so that in case any future, if any participant would like to connect with you,
Yes, sure, sir.
at least your email ID, can I type, sir?
Yes, sir. Sure, sir. Thank you.
Okay, sir. Thank you so much, sir. Um, on behalf of participants, I wholeheartedly thank you. And on behalf of KLS management and on behalf of our principal, Dr. V.A. Kulkarni, sir, I'm grateful to you for delivering such a wonderful talk on the topic nanobio interfaces. And indeed, it is great opportunity for all of us to know how nanotechnology links with biology. That's indeed a great. Thank you so much, sir. Thank you.
Thank you, sir. Thank you. Thank you.
Thank you, sir. Now, our next speaker on the board is Dr. Arun S. Nisim Gowda. Arun sir, can you switch on your video, please? Sanaikar sir, you can stop sharing your PPT.
Stop, sir. I think. Is it visible still?
It is still visible, sir. Arun sir. Yes, sir. Good evening, sir. Arun sir, can you share your PPT? Yes, sir. Yes, sir.
Can you hear me now, right?
Yes, sir. I can hear you, sir, clearly.
Okay, okay. I'm joining from two devices.
Okay.
Okay. So, shall I share my screen?
Yes, sir. Please, sir. Please.
Okay. Now I think it's visible, right?
Yes, sir. Yes, sir. It is very much visible.
Okay.
It is very much visible. Yes, sir. In a slideshow mode, sir. Is it in slideshow mode?
Yes, it's in the slideshow mode.
Okay, sir. No problem, sir. Then. So, dear participants, here we are in the last session of the 6th day ATAL FDP program, and the last session will be delivered by Dr. Arun S. Nisim Gowda. Dr. Arun S. Nisim Gowda is a research scientist, electrolyte and computational chemistry division at Ola Battery Innovation Center, India. Completed his PhD in physics from Karnataka University, Dharwad, under the able guidance of Professor N.S. Sankeshwar. Research experience at UNSIT, South Korea, IISc Bengaluru, and Indo-Korea Science and Technology, Bengaluru. His research areas include lithium-ion battery electrolytes and additive chemistry, DFT and MD simulations for materials and electrolyte design, 2D materials like graphene, nanoribbons, INSC, monolayers, etc. Thermal transport, phonon engineering, and atomistic modeling also includes in this area. Cylindrical cell mechanical design and tolerance management is also one of the areas of his interest. Notable contributions are led the electrolyte development program integrating high throughput computation, ML and experimental validation, developed novel electrolyte additives, flame retardant molecules, PTFE stability modifiers, active collaborator with suppliers, academic partners, and HPC and quantum teams. Published several articles in high impact journals like Advanced Energy Materials, Advanced Function Materials, ACS Nano, Materials Today, Nano Energy, Physical Review B, Carbon, JMCA, and others. He has 1450 citations on Google Scholars. His expertise include DFT-MD simulations, electrolyte formulation, ML-assisted materials discovery, HPC reverse resource management, battery testing and validation, patent drafting, and large format cylindrical cell design. With these brief words, I now request Dr. Arun S. Nissimgowda to carry on his presentations. Sir, over to you. And thank you very much for accepting our invitation to be part of this ATAL FDP program.
Thank you, Galgal sir.
Thank you, sir.
So I am audible, right?
You are audible, sir.
Okay. Sorry, I think now it's audible, right?
Sir, now it is audible, sir.
Okay. So, thank you very much for giving me this opportunity to present here. So I'm going to present on the emerging 2D materials and their application through a computational approach. Myself, Arun Nissimgowda. I'm working here in the Ola Battery Innovation Center, Bengaluru. So before going to this presentation, I want to give a brief introduction towards what are the materials like bulk material and what are 2D materials and zero dimensional materials like that. And from there, I will go to what are the emerging 2D materials are in the world now existing. So we can see that here, these materials are classified in different dimensional wise. The first one you can see a 3D material where you can see that the electron, usually the material consists of the electron motion only, like along X and Y and Z direction. In 3D materials, these electrons will flow freely in all the direction. Like for example, if we consider Kx, Ky, and Kz, and then okay, so that when we confine means when we restrict another direction of electron motion, then we can get a 2D material where we can exist the electron will be moving from X direction to Y direction very freely. But when the third direction, maybe it is completely confined, means the electron has a certain potential. It will not move freely there. So such materials are, we can call it as a two-dimensional materials. When again we restrict along the two direction and allow electron to freely move in only one direction. For example, here the Kx, Ky, and Kz are the directions of the electron flow, and we are restricting from the Y and Z direction, and we existing with the Kx. Usually the 1D materials are like carbon nanotubes or quantum wires, like that. When we restrict in all the three direction and we come up with the zero dimensional materials where in all the three direction, it is confined. So you can see that when we confine it, that these the motion as well as the energy density of those materials will be completely changed. We can see from here this the density of states along energy we have plotted. For the 3D, it is like a parabolic thing, exploring increasing the energy with energy. When we restrict, and that this two-dimensional material has a discrete energy states with a step-like behavior. Whereas for the one-dimensional case, this we can see the density of states is completely reducing, decreasing with energy. And similarly, again, for zero-dimensionally, we can see a continuous discrete density of states functions. So this is just for a general dimensional classes for the nanomaterials. What will happen when we go to a carbon materials? So this is a carbon-based materials, and we can see that the best 3D carbon-based material is example is graphite, or maybe you can consider a diamond also. It's a bulk type of. You can see that this graphite is a layered structure. So when you this is previously the nobody thought of making a two-dimensional material from the graphite, but in the 2004 the two people have realized that okay, this can be made as a two-dimensional material, and that I'll come to later slide. And we just understand what are the different classes of materials in carbon-based materials. For example, you can consider graphite as a 3D, and two-dimensional sheet of graphite, you can call it as a graphene. And when you roll this graphene, you can end up in carbon nanotube, where you can see that electron will can be moved along freely along the length, whereas the X and Y are confined. So if you confine all then we will end up within a fluorine. This is another you can call buckyball, and this is another zero-dimensional. Okay, now we will focus mainly on a two-dimensional material, and from when it has been realized, we will try to understand that. So the graphene, which is a two-dimensional material of the graphite, and which has been monolayer graphene is isolated via mechanical explosion in 2004 by the two people, that is Gaim and Novoselov. So you can see that Gaim is a professor and the Novoselov is a PhD student during that time, 2004, and they have come up with the first stable 2D crystal structure. Before that, nobody has realized the 2D structures. It is because earlier the whatever the two-dimensional materials are quasi two-dimensional materials. Like if we consider quantum well, where we have heard about the gallium arsenide or gallium nitride quantum wells, but they are not perfectly 2D materials. But graphene is a completely a perfectly two-dimensional material where there is no. Hello, can you hear me, right?
Yes, sir.
Okay.
Yes, sir. It's audible. Yes, sir.
Yeah. So this graphene is a completely perfectly two-dimensional material. So there is no movement of electron in the z direction. So it is perfectly x. The electron is completely moving in x and y direction. That's why it is called a perfectly 2D material. So this is you can see that a sheet of single layer honeycomb, single atomic thick carbon atom. So what happens when we have this only perfectly two-dimensional material? It is completely a different electron behavior we observed in the graphene, especially in graphene. Usually in semiconductor, these electrons have a certain mass, But when it comes to the graphene case, these electrons become some massless, means they are moving at the speed of almost near to the lights. So that's what you can see a cone, a perfectly a linear dispersion of the band structures at the K point. These K points are called the Dirac K points. That is the speciality of this graphene graphene, and that's why this, because of this Dirac cone of behavior of the electron, it has a really high conductivity, electrical conductivity, as well as a uh, phonon conductivity, means lattice thermal conductivity. That may be used for a real good applications. And similarly, in the graphene, when you stack another layer of graphene on the top of the single layer, then we will come up with a double layer or a bilayer graphene. But when you stack another layer of graphene on the one-on-one, their again property drastically changes. You can see here, this is single layer graphene. You can see a complete Dirac cone band structure with a zero band gap. When we stack another layer of graphene, this band structure splits into a two layer. A small narrow band gap is opening. When you apply another like electric field along along this direction, z direction you can call, then this band gap opens with a large gap. So with these things, we can tune the property of the graphene, whether we want a zero band gap graphene or with a certain band gap graphene, we can tune it accordingly and we can use it for the different application. Especially these graphene are used for the transistor case. But there is a difficulty as of now. The replacement of the silicon has not yet with graphene. So this graphene and bilayer graphene has led to a invention of the different two-dimensional materials. This is what I discussed, the electrical conductivity and the thermal conductivity of when we compare to the different semiconductor, for example, silicon, germanium, gallium arsenide. The electrical conductivity is really high. You can see that it is order of 10 raised to 6. This is a log scale. It is almost 2 orders of, not 2 to 3 orders of higher than the silicon, which we are presently using in the transistors. When you can think, if you replace with a graphene, then it will be really a good one. But people still wanted to go with the silicon only as of now, because it is a huge challenge in industrialization. At the same time, if you see the thermal conductivity of this graphene, this is really higher compared to the known metals, that is copper and aluminum. Even it is higher than the diamond, almost 2 times higher than the diamond. So these properties has led to invention of the new two-dimensional materials. The people and the researcher are involved in the finding out a new types of materials. So in that case, the people have moved to a new type of transitional metal chalcogenation. In short, we call it as TMDs also. It has a combination of a metal, transition metal, and chalcogenized. For example, if you case, this is a formula of these TMDs, M and X2. The M has a different transition metals. You can see these are the transition metals. And here is the chalcogens. And you can see the structure of these here. The layered structure. These are also layered structure with the formulation M into X2. The M is the transition metals such as transition, molybdenum, niobium, vanadium. And whereas for the chalcogens, it can be a sulfur, selenide, or a telluride. So, but in these two-dimensional materials, it has a zero band gap. It has certain values of the tunable band gaps. You can tune these band gap. For example, you can see there are in these 2D materials also there are three types of crystal structures. Like means you can see that different symmetries depending on the different stacking, one on one. See here you can see that it is a single layer of TMD. It is called 1T structure. When you stack another layer of TMD, it is called 2H phase of this two-dimensional. And similarly, when you keep 3 layers of this, then it is called as a 3R. And correspondingly, their band structure also changes. You can see that the band structure of here for only one layer means if you consider 1T, this is a direct band gap semiconductor. When you move to a 2 layer, that is 2H and 3R, this band gap is moving. Means you can see that this is a band gap. This is a conduction band and valency band, and you can see a shift is happening. This type of band structure is called indirect band structure. This is a direct band structure. Okay. See, and we can see that there are different two-dimensional TMDs are already synthesized. For example, this is a most famous MOS2. This is the first TMD which is synthesized after in the year of 2010. So you can see that it has a direct band gap of 1.2 electron volt, and if you go for TIS2, it is the band gap is 1.3, and another very famous TMD that is WSE2 and WS2. It has a so you can see that these have a large band gap we can use for the optical properties studies, and whereas this MOS2 is used for most of the transistor. And these two-dimensional and graphene has led to invention of another type of two-dimensional material, which is really getting famous nowadays. That is called MXene. These MXenes are rapidly growing two-dimensional transition metal carbide. This is carbides. Those are the TMDs are the chalcogenides. This can be a carbide, nitride, or carbonides, and it has a formula. It can be Mn, Xn, and Tx. This was synthesized first by Yuri Gogotsi, and he's a very famous guy. He synthesized MXene in 2011. And you can see that there are different possibility in MXenes, a 2-layer MXene, 3-layer MXene, and a 4-layer and 5-layer. So you can see a different combination also. Here, this transition metal can be mixed up with a different transition metal and with a similarly a different surface functional. So that's why it has many possibilities compared to the graphene TMDs, and that's what it is gaining much attention at the present year. You can see from the this is a Yuri Gogotsi Google scholar, and you can see that this is the first paper came in 2011, and you can see that around 12,000 citations for this paper. This is the first MXene, that is Ti3Al C2. This is from the max phase. They have arrived this thing. Another paper which is on the MXene, which is again came in just in 2002. Within 2 years, it has almost 7,600. And see, you can see the citations almost 3,28,000. Within like after 2020, this is almost 2 lakh. Within 5 years, you can see there's so much of citations are happening because of the MXene's inventions. It has gained much more attention than the graphene because these MXenes have a much more wide application because of variety of MXenes are applicable. You can see that this MXene can be found by different combinations. Like for example, M2CX2, we can make with a scandium, titanium, vanadium, chromium. Like so, several combination can be made with these combinations, like with, you can see that here. And also mix matching these like different transition metal, also we can come up with a different maxim. So that's like around 1,000 maxim structures we can synthesize, and with the different properties. That's what it's really a wide opportunity for everyone to explore the maxim, and for different application, like for example sensor application, optical properties, and these things, even for battery application also using the maxims case. So you can see here year wise the route of synthesis of these maxims also changed. In 2011, the where the Yuri Gogotsi has synthesized, um, it was done by synthesizing by HF etching. They taken the max phase of the max scenes, and then they have laid out the aluminum, and then they arrived at these maxines. So like then with the year go on, year changing, the people are inventing a new route to synthesize maxines. Like people try to grow with the CBD method also, tape exfoliation, like how the people exfoliated the graphene. And similarly, different methods like alkali chain, Lewis acid, this thing. Like people trying to explore these maxim with a different synthesis route and efficiently getting these maxims. So with these backgrounds, so I will try to go to my research area where I have done the applications using the computational approach. So what is the computational approach? What we are doing it? See, mainly we are doing this study of these 2D materials with a use of density functional theory. You may be heard about it during your research time or within the masters. Maybe you have heard about this density functional theory. So I'm mostly using this DFT codes and theory to understand the property of these two-dimensional materials. So I will give a brief introduction about this computational approach, that is especially density functional theory. Maybe who is not knowing about the DFT, I will briefly give the introduction about these things. So density functional theory is a computational and mechanical modeling method used in physics and chemistry and materials. DFT uses Schrodinger equation only to solve the behavior of the electron in a system. So like during our masters, we used to solve the electron wave function using the Schrodinger equation, but that is for only single electron. But here with a DFT, we are used to solve the Schrodinger equation for many electrons. So this was first developed by the Kohn and Sham in 1964, and they minimized this ground state with the function of charge density. They approximate this electron as a electron wave function as a charge density and minimize the energy density. You can see this is a usual Schrodinger equation and the Hamiltonian for different for the electron, nucleus, and long range potential. So this can be simplified by writing a Stern and Kohn and Sham equation in terms of the energy density and the potential energy density. So here you can see that this how we solve this density functional. We first consider the Schrodinger equation and we try to find the different trial function for the density by optimizing the potential and different lattice structure, and we optimize the geometry and then calculates its potential energy and then solve the Schrodinger equation. And then we arrive at a certain eigenvalues. If it is we get a converged value, then we proceed for the analysis. Otherwise, we again repeat this step. This is how the DFT works. This is a workflow. To do this DFT, we have different software packages. Some are licensed one, and some are open source. So open source means which are freely available, which can be used. For example, so again, like these DFT codes are different for different type of materials. For example, I want to do for a crystal structure, like a two-dimensional material, which has a perfect boundaries, perfect crystal structure. And like another DFT codes are there where used for the molecules, like Gaussian and Orca. Those are for the which don't have a proper periodic boundary condition. For that, we are using Gaussian and Orca. Gaussian is a licensed version and Orca is a open source. But here, whatever I have shown here, these are the DFT codes for the crystal structure where it has a perfect periodic boundary. This is not for the, these are codes are not useful for the molecules. So WASP is a license version where we need to pay and buy it. Whereas for the quantum espresso, it's completely free. You can use it. Like anybody can use it and do the DFT calculations. Similarly, like there is a Berkeley. These type of codes are used for different. What is your purpose? What properties you wanted to understand? Accordingly, you can use these DFT codes. The main problem with these codes is that you need a high computational power. Like we cannot run these codes in our laptop or our in desktop. So we need to have a high performance computing facility. Then only we can use for the solving any, understand any property of the material. So here I can show how this DFT package works. So we usually model the structure. Like for example, I want to understand some property of any material, like a graphene I consider, or a TMD or a Maxine. First, I need to model it. It may be wrong, or you need to try it, and then fed to a high computing facility using the DFT code, and we'll find results like its band structure or a density of states, and we can correlate with its absorption coefficient for, like, if you want to study the optical properties. So for example, here you can give a different input structure, like if you want to understand the defect engineering, you can create a defect and model it and again do the calculations. So like I told about you, right? This to do these calculations, we need to high computing facility. So previously, whatever my work has done, I use these high computing facilities, especially when I was in IIC Bengaluru, where we have a supercomputing facility. It is called Sahasrat. It is also this machine is called Cray. Yes, we can use, like for example, in our computer, it is may hardly 8 cores, means 8 CPUs in our laptop. If you high computing, like in these supercomputing facilities, maybe the CPUs may be 1,000 to 2,000 or 3,000 cores. So you can utilize these number of cores and you can do the calculation within 1 hour or 2 hours. Sometimes with using these facility also, it will take 2-3 days also, sometimes a week. So you can imagine whether it is possible to do with a single our computers. So when I was in South Korea, I used this KIST, and also I use a Chinese supercluster, and this is a Thinhe 2. This is the fastest supercomputing facility in 2021. But now another supercomputer has fastest in the world. So with this background, I will start my study for the whatever during my research work during my postdoc. I am presenting here. I am not showing any results of my present work. where I presently am working on graphene, the battery materials, which are confidential. So I am not showing those results. So I'm showing only those which I have done during my previous journey, research like a postdoctoral research and some research scientist in my previous institute. So here I consider a two-dimensional material of gallium selenide. I try to understand the band structure of these materials. You can see that this is a structure of this two-dimensional material. It is a layered one. You can see this is a indium and this is sulfur. This is gallium and sulfur. And this is a electronic band structure. You can see it has a band gap. This has around band gap of 2.1 electron volt, which may be good for the optical properties. And we wanted to understand what is the thermal conductivity of that. For that one, we obtained the phonons. This is a phonons. Phonons means it is the lightest vibrations. To understand the thermal conductivity, we need to understand its phonon, means lattice vibrations. We can see these are the acoustic phonons, longitudinal phonons, and optical phonons. So from this one, we can understand how much it is giving to the contribution to the lattice thermal conductivity. Similarly, you can see a band structure for gallium and indium and selenium. This is the corresponding crystal structure for that one. So you can see that corresponding phonon structure for gallium selenide and indium selenide and gallium Se and NEMC. And correspondingly, I have calculated the lattice thermal conductivity as a function of temperature. And we can see that gallium selenide, which has the highest thermal conductivity compared to the other transition chalcogenide. So this to understand this one, why these are not contributing to the high thermal conductivity, we try to understand its scattering. Means the phonon is scattering by the another type of phonons that we can understand from the scattering rates here. So we can see that so the green one, which has a low scattering rates, that has led to a high conductivity. So, and we try to understand what is the reason for this low conductivity of these materials. Then we found that there is a anharmonic, means lone pair electron existing at the selenium site, which has led to a anharmonicity arising from these lone pair. So that has led to a low thermal conductivity in indium selenide and these materials. You can see here. Okay, with this one, I will move to application of towards catalysis. You may be knowing what is catalysis. I will just briefly give introduction about these catalysis. So see why we are doing catalysis here. So there are many types from the catalyst we can do or extract different sustainable energy. For example, H2O we can use, and we split H2O into a hydrogen and water, or this is called water splitting. This H2, the splitted one, we can use a hydrogen storage, and this hydrogen storage can be used for our fuel cells. And again, for this like CO2 reduction, when you use this CO2, and then we can use for the biomass, and this type of CO2 can be used for the again running some energies, and I will go through those things in detail. So I told about the water splitting, means we are splitting the water. Water contains hydrogen and oxygen, right? In order to get hydrogen storage, we need to split this water so that we can get hydrogen. The one of the method is called hydrogen evolution reaction. Another one is oxygen revolution reaction. So in the hydrogen revolution reaction, we get the hydrogen, and in the oxygen evolution reaction, we take out the oxygen. So in order to get this one, we need, this is a simple setup of electrocatalysis. You may be knowing it, where one side is a cathode, another side is an anode. We coat this anode with a catalyst. So to speed up these activities, that is HER and OER. To speed up this catalyst, we need to find a different materials.